All right, good morning. Welcome back to day 2 of our North America Partial Discharge Symposium. I see quite a bit of people are still joining in, so welcome back from yesterday. We had some great tutorials that were presented from our team, Mathieu and Mathieu. They will be joining us today again as well and supporting the moderation for Q&A. And I am Parisa Jalalipur, Regional Marketing Manager for North America. So before we get started, I'm just going to go over a few intro slides like I did yesterday, and then we will jump into the great agenda that we have set for today. All right, so as many of y'all have seen while y'all have been waiting before the event or even during the break, we've had a bunch of photos, different photos, slideshows and stuff, and most of them were of our OMICRON Academy that's actually here in our Houston location. So yesterday I showed that we are a global company, but we have local support within North America. So we have our Houston office, which I am located in, and as you can see here, some snapshots of our training facility. It's an indoor substation, and we hold quite a bit of training courses. This week we actually have double training courses happening while simultaneously. So it's really great to have people come to the facility and really see it. And then we also, as I mentioned, will have Mathieu and Mathieu joining us from the Toronto office, which is another local office we have here in North America. So yeah, so if you're interested in ever joining any of our trainings or anything, please let us know. We will be having the survey again after today's session. So thank you everyone who did fill out the survey yesterday. Again, we really appreciate and value y'all's feedback. So if you do have any questions or you're interested in joining any of our training courses, let us know and we can give you more information on that. So yesterday, I also mentioned that there are 3 main things that we focus on here at OMICRON, which is innovation, customer support, and sharing knowledge. So here you can see a list of all of our knowledge sharing, all of the different platforms that you can kind of stay connected with us. So we have, again, as I mentioned, our OMICRON Academy, different sessions. We have live interactive webinars that are available. We also have a LinkedIn page. If you're not following, please check it out. We have close to 54K followers. And then we also have an OMICRON Energy YouTube channel. And here you can find a list of different videos of like our applications, our products, and things like that, and different training courses. So definitely check that out. We also have our OMICRON customer portal, and this is where you can really stay up to date and just hear the latest and greatest of what's going on. And we keep our customer portal area updated. And yeah, so if you want to join that, you would just go to my.omicronenergy.com. And then we also have more OMICRON hosted events. So this event is an OMICRON hosted event where we support, and we have several other ones throughout the year. And most of them are, we have a variety. So we have some in person, some virtual, and we've also done a few hybrid events. So as I mentioned, we do have our facility here in Houston, and so we do have our hybrid events here live from our Houston office. And lastly, we have our podcast, which is our Energy Talks. And this is something that we really stay up to date with. And it's really cool. It's really cool to hear all the different topics and things like that that we have available with the podcast. So it's really, we have this great list, and we'll share it again at the end of today's session as well. So if you'd be interested in checking any of these out. So I just saw a question come in about the survey. So we will be having the survey. It will pop up at the end of the session. So once you exit out of the platform, the survey will pop up on your web browser. So we've noticed that that is really easy for the team to just have it pop up, and you can answer the questions. So yeah, so it's just really important to let us know your experience, any topics that you like to hear in the future. if you'd like to speak at another speak at an OMICRON event, or if you just want to be contacted by us, you can definitely put that information in there. And as I mentioned, thank you again so much to everyone that did fill out the survey yesterday. We did get quite a list of responses, so we really appreciate that. And we will have the survey coming out again today at the end. So just a little bit about your webinar setup. So all mics are muted for all the attendees, and we will be doing Q&A after each presentation, and that will be moderated by Mathieu and Mathieu. So if you have any questions that do come up, please put them in the Q&A section. So at the bottom right-hand corner, you'll see a button that says Q&A. And if you click on that, you can put in your question and just make sure that you send it to all panelists. So that way everybody can see the questions that are coming in and make sure that we don't miss any questions. Also, your layout view. So my team has the layout already set up for everybody. However, if you'd like to adjust it based on your setup at home or at the office, you can change that by going on the top right-hand corner where you see the videos and just click on layout, and then you can adjust it for what would work best for you. All right, so now we can get into today's agenda. So yesterday we also got a question about the agenda and where they could find it. So the agenda is also on the website. So we'll put that link again into the Q&A. So that way, if y'all want to go ahead and take a look at that throughout the sessions, you can. But here's the agenda for today. So we're going to be getting started on proposal for bushing cooldown partial discharge test, and then we are going to have a presentation on lab considerations for partial discharge testing. Then we'll jump into a high voltage partial discharge filters for field and factory testing, and then we will be taking a lunch break, and that will be about an hour. We aren't going to close the event, so the event will still be live and happening, so feel free to stay on the line, but you can just take a step away for that hour, and we will have a countdown so you can see how long you have until we get started again. And then after that, we will come back and jump into a presentation on challenges in testing medium voltage cable in a field environment. Then we'll go into diagnostic integration for commissioning of critical power cable systems. And we will end the day with a practical aspects for PD measurements on Stator coils and bars. And then we will, and as I mentioned, we'll have the Q&A happening after every presentation. So throughout the presentations, please feel free to put your questions in the Q&A section so that way we can answer them accordingly. And then we'll have just a quick closing from myself, and after that, we will be ready to end the event, and the survey will pop up once you end once you leave the platform. So now we're going to get started, and I'm going to go ahead and pass it on over to Mathieu to introduce our first speaker for today. And yes, thank you again for everyone joining us, and I will pass it to y'all.
Right. Thank you very much, Parisa. And thank you for all the audience again today for joining us for the symposium. We hope you had a great short tutorial with us yesterday, right? That was on the cable testing part, which we're glad that we were able to show some of the measurement technique for PD testing on cables to you before. Now today, the first session to kick us off is a speaker from Germany, Egon Kirchenmayer. Egon graduated from Technical University of Munich and joined Siemens in 1990. He started as electrical design engineer for power transformers, has since held various positions in Siemens, including head of mechanical design team, electrical design department of transformer in Nuremberg, and as consultant for electrical design in other Siemens locations worldwide. He also supports Siemens as project manager for merger and acquisition worldwide, conducting market studies and business planning for new transformer factories. Apart from being the head of global operation support for large power transformers, Egon is a member of various working group in IEEE since 2011, which is where we met in the IEEE working group, as well as being in the VDE working group and European Committee of Electrotechnical Standardization Group. Fun fact about Egon, he speaks 4 languages, German, English, Spanish, Romanian fluently as well. Today, he'll be presenting a proposal for the bushing cooldown PD test, which offers a new angle to look into the process as well. So let's join me and welcome Egon to be our first speaker. And Egon, the floor is all yours.
Good morning, everybody from Germany. Thank you, Matthew, for doing this detailed presentation and introduction to myself. So, as said, I work for the company Siemens Energy, and mainly in the area of transformers. So we have around 20 transformer factories worldwide where we produce transformers, and in most of them large power transformers. And every transformer has bushings, of course, and let's say the oil field transformers, they are mainly 3-phase transformers, as you know, and they have at least 6 bushings, 3 on the high voltage side, 3 on the low voltage side, and in most cases also bushings in the neutral, and maybe even in tertiary windings. So every transformer which is oil filled is equipped with a lot of bushings. And of course, we need to rely on this equipment and be sure they work safely and they don't disturb our testing and they don't reduce the lifetime of our transformers. And being responsible to support our factories, I also work a lot with problems which we have and try to solve them. And also bring many topics into the IEEE community and try to make the guides or adapt them in case where we think it could be required. And in that regard, we started this discussion about proposal for a bushing cooldown partial discharge test. And the reason for that is that having so many bushings on every transformers, we saw that especially in the US, where it is required to do the electric tests in many cases after the heat run test. And this creates sometimes problems in the bushings. So first we have, let's say, the heat run test of the transformer where we load it with a lot of power and we heat it up. And then later it cools down relatively quickly. And then we are supposed to start the dielectric tests of the transformer right after this cool down, or sometimes even when it is cooling down. And what is happening here when the bushing cool down, because they are exposed to air also, it seems that there is an oversaturation of the nitrogen which is filled into the head of the bushing, and an oversaturation of the oil, which is enriched with nitrogen. And this can produce bubbles in the bushing itself. And these bubbles, of course, will be detected during the partial discharge test. And even we had cases where these bubbles are so severe that they were there when we did the impulse tests, and even we have damaged some bushings. And you can imagine that this will create a lot of trouble and a lot of problems when we test our transformers. First of all, we have to pass the test successfully, right? We cannot accept partial discharge inside, but we have the partial discharge in the bushing, and you cannot separate them. And the bushing manufacturers, they propose some procedures, which is now under discussion, to be included also in the IEEE guides. They propose to vent these bushings and open the venting cap, and this would help to release some of the bubbles. But we know it's not 100% safe and will not solve the problem 100%. And therefore, we propose here a test in IEEE where we simulate, let's say, the heating and the cool down of this bushing, and then make a partial discharge test right afterwards to prove that this bushing design will not produce this problem, that it creates bubbles and partial discharge after cool down.
Hey, Egon, I'm so sorry to interrupt. I just wanted to check, are you going to be changing your slides?
Yes, this is exactly what thanks,
Okay,
Marisa. I
perfect.
was thinking to give this introduction, right?
Oh, I love that. Yes, I just wanted to make sure that you were all
before
set. Okay.
thanks a lot, really. Thanks a lot. Yeah. Of course, now let me try if I can control the page. Oh, it seems I cannot. Ah, it works. Thank you very much. Okay, so that's the title. That we propose a test to prove that the bushings are free of this partial discharge. And here you can see again a description of what we are talking about. On the left side, I'm not sure if you can see my mouse. Yeah. Anyhow, on the left side you see let's say a drawing of the top part of a bushing. This is the OIP bushing, we call it. It is oil immersed paper insulated bushing. And what you see is you see brownish on the sides. You see the porcelain of these bushings. And you see, let's say, the head of the bushing, which is normally of metal and sometimes of glass of some manufacturers. And you see that this bushing is filled with oil, and you can also see in green where that the oil does not go up to the top level, right? The oil stops somewhere, and then we have a nitrogen cushion on top of the oil. And this is needed because if the bushing heats up, the oil will expand, and so the expansion then is taken by the nitrogen cushion. So if there would be no nitrogen there, the pressure would increase dramatically inside the bushing, and it would break, right? And therefore we have a pillow of nitrogen. So when the oil expands, so this nitrogen is compressed. And so the oil level can raise a little bit, and the pressure does not increase too much. So it increases normally around 10 psi, right? Up to 10 psi, depending on the temperature of the bushing and on the design of the bushing, of course. And just want to explain what happens. Why do we have, let's say, problems in gas bubble evolution? So as you see here, we have the bushing filled with oil, and we have the nitrogen pillow on top. And what happens if the bushing is stored for a long time? Then the nitrogen will be partially dissolved in the oil. And this process will take as long as the nitrogen is saturated, or let's say like this, the oil is saturated with nitrogen, which means there is an equilibrium state which is reached. And that equilibrium state can be very different. It depends on many factors. One factor is, of course, the type of oil which is inside and the type of gas, but the gas is mainly nitrogen in most cases. Sometimes it is air. But also it depends on other factors, right? And these other factors, the most important is the temperature. So as higher the temperature, as more nitrogen is dissolved in this oil of the bushing, and it depends on the pressure. So as higher the pressure is, as more nitrogen is dissolved in the oil of the bushing. So now we know that, let's say, the transportation and storage time can be quite long. It can be a few months. So in this time, the bushing oil absorbs already nitrogen based on the conditions which are there, which is the ambient temperature normally, where the bushing is stored, and based on the pressure which is inside this bushing. So when we then do a heat run test of the transformer, which means we heat up the transformer and also the bushing is heated, then the oil of the bushing will start to absorb more nitrogen than before, because the saturation level of nitrogen in oil is higher at higher temperature, right? So bushing will start to absorb nitrogen. And then later, when the transformer cools down and the bushing cools down, then the saturation level reduces because the temperature of the oil reduces during this cool down. And then the excessive nitrogen, which was there in the oil, needs to get out, right? Because we have so-called oversaturated oil with nitrogen. And then how shall this oil get out? This nitrogen gets out. It gets out like in form of small bubbles, which then are released, and finally they will get out. It's the same effect which you know when you have a bottle of sparkling water, for instance. When you open the cap, then you in a sudden reduce the pressure, right? You don't change the temperature, but you reduce the pressure in a sudden. And all the gas which is stored in the sparkling water, let's say all the excessive gas there will be released in form of bubbles, right? And these bubbles, you see them right in a sudden. In the bushing is like that when they cool down, bubbles start to form. First they are small, then they get larger, and finally they get out. So this is the problem which we have. So if we have bubble in oil, oil is an insulator, or if we have bubble in the body of the bushing, which is paper insulation, this is very bad. And as you know, bubble does not have the same electrical withstand capability like oil. The discharge voltage is much lower. So the bubble was not there before, and it is there now during the electric testing. And therefore, some small partial discharge can happen in these bubbles. And these bubbles even they get larger as long as the bushing cools down. We will have more partial discharge. And also, once the partial discharge starts in the bubble, also additional gas can be produced. So, you know, discharge in bubbles is a discharge of low energy, but still it has enough energy to produce a little bit of hydrogen and transform a little bit the oil into hydrogen, right? So this means we don't get only the bubbles coming from the nitrogen, which is absorbed, but also we get bubbles formed by decomposition of the oil. And this is what can happen in service, for instance, right? And can be very bad in service, right? Because not only during testing, as I said, when bushing cool down, we can have partial discharge, which disturbs our test, but also in service. Let's say if there is a sudden cool down, we will get partial discharge in these bubbles. And the important thing is that this process should stop. The bubbles should be absorbed by the oil, and then the bushing is healthy again, and it can work very well. We know this from experience. But there can be cases where the discharge is self-sustaining, and then it continues to form bubbles, and then the bubbles will never disappear at service voltage. And then the bushing can get damaged. Also, there are cases known which happen like that. And the risk for this in service is especially in applications where we have cyclic loading. For instance, in the new solar stations, there we have a cyclic change of temperature of the transformer and of the bushing, right? Because the ambient is cyclic changing. And also during the day, when we have the highest ambient temperature, we have the highest loading normally because the solar power is maximum. Then the bushing is also heated maximum. So then during the day, we have the maximum heating of this bushing. And during the night, there is no load. The ambient is low, so the bushing cools down rapidly. So then in solar application, there is a high risk also to have bubbles. And each design must be such that no sustained bubbles are there in service, which will harm the bushing itself and can lead to degradation and the failure. So for all these reasons, we feel it's very important to have a solution. And what we propose is to do some tests in advance at the bushing manufacturer location to make this test and make sure that we know which bushing is not prone to produce bubbles, because it depends, of course, on the design of the bushing. And we know some designs, they don't produce this phenomenon. And we know others do that. And so in that regard, just to prove this by a test, therefore we have developed the test procedure. So now I would like to show you what we measure in some cases. So this was a transformer which we tested. We made the heat run test. It was heated up to just 72 degrees, the transformer top oil, which is not too much. And then it was cooled down with fans because the transformer had fan as a cooler. And during the subsequent induced test, then in all 3 low voltage bushing of these transformers, we saw partial discharge. You see it on the right side, you see the partial discharge patterns. So you see also the voltage to ground of every bushing, and you see that the partial discharge starts a little bit before voltage 0, and then produces these typical arcs, which you see there, especially in X1, X2 phase, you see 2 arcs or 3 arcs even, right? In X3, you see some arcs which start, and in X1 also you see one complete arc at least at the negative polarity and the same at the positive polarity. So this shows for us clearly, this is an indication that we have bubbles of different sizes inside this transformer. Then we were looking how the partial discharge develops. You see now with 3 colors in every phase how the PD developed. And you see that if we keep the voltage constant, the PD starts to slowly increase continuously, right? And this is typical also. This means this shows us that more and more bubbles are produced and more energy is there for the partial discharge, or also more and more increases size of certain bubbles who produce the problem. And then even if you reduce the voltage, you can see that the so-called extinction voltage, right? It's very much lower than the inception voltage, right? Inception voltage, as explained yesterday by Mathieu, right, is the voltage where PD starts. So here it starts quite early, but also the extinction voltage is normally much lower than the inception voltage because all the bubbles which are not there at the beginning, they are now there at the end. And it's very difficult to extinguish this partial discharge. So now the bushing manufacturers, they recommend to us that we should open the cap in the head of the bushing, right? This is called venting cap. So it's not so easy to see, but normally on the head of the bushing, there is a small cap which you can open. And then the nitrogen in the bushing is in contact with the outside air. And then we have an equalization of the pressure. Normally, when we start the test, I will show you later, in most cases, right, there is under pressure in the bushing because the bushing oil has absorbed nitrogen and therefore the pressure decreases, but I will show you later this. And therefore, when you open the cap, there is a sudden increase of pressure, right? Because there is equalization of pressure with the ambient, which is higher than what is inside. And in that case, if the pressure increases, the bubble size will reduce. And here you can see what happened when we did this test after opening the cap and venting the bushing. And you see that the partial discharge has reduced a lot. So we have a lot of spontaneous PD, right? Which are some bubbles which are there, which move maybe, and then they move out. But there are not so many bubbles generated anymore, and there are not so many bubbles there as in the first test. So it has improved a lot, the partial discharge behavior. So the partial discharge is now below the limit of, let's say, 80 picocoulomb or 60 picocoulomb, difficult to say in this picture. And so in this case, we probably would be able to start to test the transformer. But there are cases where this discharge does not disappear. And then sometimes we have to wait a few days. We have to send the customer to its home and to come again in another day. So you can imagine a lot of disturbance and a lot of cost involved. So of course we want to avoid this. And therefore we want to know which bushing is prone to produce this and then to select bushings which are suitable. Okay, so with this, I hope you understood our need to have bushings which don't produce this partial discharge during the testing, right? And also you hopefully understood that opening the cap does not always help on short notice to have a partial discharge-free bushing and also partial discharge-free transformer. so that we can be sure that we can see also if there is other discharge mass which is inside the transformer and not inside the bushing, right? So that was our motivation. And then we proposed this test, which should be done at the factory of the bushing manufacturer. And we proposed to put a bushing at a temperature rise to ambient, which covers the transformer final acceptance operating test condition. And then wait until the bushing is saturated with nitrogen. And then let the bushing cool down to ambient and create this oversaturation, which I have just explained. And then, of course, bubbles would be generated in case the bushing produces bubbles. And then perform the electric test of the bushing and measure the partial discharge activity of that bushing to see if it is free of partial discharge or if it produces this problem. And as I said, not all bushings produce this problem. It depends on the design of the bushing, because if the design is is good enough, then even the cool down is not strong enough to produce large bubbles, which can be detected during the partial discharge test. So the procedure can be done like this. So the bushing manufacturer could put a bushing in a heated vessel, for instance, in a room with controlled temperature. And depending on the size and the design, you have to wait till then the oil is saturated with nitrogen, right? Because if you have a new bushing in the bushing manufacturer side, you always fill the bushing with degassed oil, right? And this degassed oil will never produce bubbles of nitrogen because there is no nitrogen dissolved in it. So therefore, you have to wait quite long till the nitrogen from the head of the bushing is dissolved in the oil, right? And this is not happening so quickly, right? It may happen after many weeks of storage and transportation, or if it may happen during transformer testing. And of course, we want that during the bushing test, we heat this bushing to a temperature which is high enough, and then keep it long enough to get this full saturation, at least 99% saturation, which could take weeks, right? But I think there is no way to avoid it. And then, of course, depending on the tolerances of the design, of course, it's better to test more bushings to be sure that all behave statistically in a proper way. And what temperature should be installed? So here this is a small discussion about the temperature which is needed. So let's say the IEEE standard says that the insulated liquid of the transformer should be heated up to 65 degrees, right? And also there is another thermal basis for rating of the bushing is the 75 degrees even, which can happen at overload. And then we have an ambient of 30 degrees, right? So, but nevertheless, we say an over temperature of 65 degrees is typical. And therefore, we propose to use this as a basis for this bushing cool down test. And here on this slide, you can see now the difference. On the left side, you can see the transformer during factory acceptance test at rated load. You see the temperatures. And on the right picture, you see what happens during bushing cool down test. So let's look a little bit to the figures, right? On the left side. When I have the transformer factory acceptance test, the ambient is 20 to 30 degrees, right? The top oil is 89 to 95 degrees. And then when the transformer cools down, there is a long time constant for cool down. You see the yellow curve. So the bushing goes down, let's say the temperature goes down to ambient after a quite long time. So the time constant is 3 to 4 hours, right? It takes quite long on the transformer. But when we do the bushing cool down test, the transformer is not there. Now you can look to the bushing to the picture on the right side. So if we heat it also to 85 degrees, we cool it up to air temperature, and the bushing itself has a very small time constant of 1 to 2 hours. So this means the cool down is much faster. So it's much a much more severe condition than if the bushing is cooled down on the transformer like it's seen on the left side, right? So the curve on the right side indicates a quick cool down, and on the left side we have a very slow cool down. So this is, we think it is important to make some preconditions which are worse than during transformer testing, so that we are sure that whatever happens during transformer testing is covered by this test, right? Now let me change to the next slide. So this yeah, now it works. So after this bushing is heated and after it is cooled down, like it was shown, then we propose to do a series of different partial discharge tests. So, for instance, we would like to do this test to begin it immediately after the cool down and do it several times in a 24-hour period, like it is shown in the picture below. There you can see first we put one cycle of transformer test. You know, transformer testing always is like this, that you go, maybe I go back to the second slide, right? You see the voltage, the blue curve is the voltage. You see you raise the voltage in steps. Then you have a small peak, which you see there, which is the enhancement level. Then you go for 1 hour to, let's say, the 100% test level, and then you reduce it in some steps. And the same we propose to do for the bushing cooldown test. So you raise it, you see the peak, you keep it 1 hour constant, then you go down, then you do after 2 hours another cycle, and you repeat this several times in the 24 hours. And the criteria would be, it should be free of partial discharge test below 10 picocoulombs, like it is the limit for bushing testing, for instance, during this test sequence. So that's our proposal for the test. And here you see practical example. We have put 3 bushings, which you can see here. You see now the whole bushing, right? You see the porcelain, which is brown color. You see the bushing flange on the bottom, which is a gray circle of aluminum normally. Then the bushing has another part, which is immersed in oil below that flange. And on top, you see the gray caps of every bushing, which is the head of the bushing. This is the cap, which is filled with nitrogen, partially normally. And then we put these 3 bushings, we put it in an oven, which you see below. It is the oven which is used normally for drying the active part of the bushings. So, and then we kept it quite a long time at the temperature of 85 degrees, as mentioned before. And you can see here a picture where we have measured the pressure inside the bushing. So right at the beginning, when you start to heat this bushing, right, the pressure was 0, but when you start to heat, you see the pressure is increasing a lot. So around 0.7, 0.8 bar, right? So this is, let's say, a little bit below 10 psi. And then after a very short time, you see the pressure starts to reduce. And this is the situation where already the nitrogen starts to get dissolved in the oil. And therefore, there is less nitrogen in the bushing head, right, in the pillow. And therefore, the pressure reduces, right? And looking, I mean, all the time we kept the temperature constant, right? It did not change, right? So, and you can see after a very short time already that the pressure reduced a lot, which means a lot of nitrogen is already dissolved in the oil of this bushing. But nevertheless, it took quite long. So really, if we keep the temperature constant, it took 3 to 4 weeks till we got a situation where we were sure that we have good stabilization and the saturation of the nitrogen of the oil with nitrogen has happened, right? And we have a stable condition. And so you see the data also on the right hand side. And so once the pressure is stabilized, we know oil is saturated with nitrogen, and then we can let it cool down, and then we can do the partial discharge test. So this you see on the next slide. So then we started to, let's say, take it out of the oven, put the bushing to the ambient, And then you see what happens. So these are three charts. One shows the temperature on the head of the bushing, the other one on the flange of the bushing, and the other one shows the pressure inside the bushing, right? And you can see what happens. Temperature falls down, and pressure also goes down. And this is exactly the situation where the nitrogen starts to be released from the oil to the nitrogen below, right? And this is exactly then the situation where we want to start then to make the tests, the partial discharge test, so that we see during all this period if bubbles are there and if they disturb our testing, right? And on the right hand side, then you can see the results of a test which has shown that this bushing was free of partial discharge, and it was also free of bubbles, right? So more or less with this, I went a little bit quickly because I was afraid time is not enough, but it seems it's enough. So just to conclude, so we think that it's possible to design bushings, oil-filled paper insulated bushings, which don't produce this problem and don't produce the bubbles. We have proven also in some cases which we tested that it's possible, like you can see here, to have designs which don't produce partial discharge. And as I said, so the problem is we want to avoid that this partial discharge inside the bushing disturbs our transformer testing. And also we want to be 100% sure that we will not have any problem in service. Now we started the discussion in IEEE, and of course there are different parties there, and around 500 people participate in these transformer committees. We have bushing manufacturers, we have transformer manufacturers, we have customers, and I saw very different reactions, right? So the customers, of course, transformer customers are very interested to have this test. Same transformer manufacturers, because they are disturbed a lot. And of course, bushing manufacturers may not all be very interested about this test, but I think we can convince them. And so there was a big discussion because the proposed test, as I've shown you here, it requires a lot of time and requires also to have an oven where you can heat this bushing and keep it heated for a long time, right? And of course, we don't ask to test every bushing, right? We just ask to test every design of a bushing. And in this way, we could specify a special test, right? And of course, our proposed test is to heat these bushings for a few weeks till we have reached the saturation. But we are working now on other methods which allow to do it in a more simpler way. For instance, one method could be to store the bushing at ambient temperature for a few weeks or months. So then we know already that we have a very good saturation of the bushing oil with nitrogen, but at ambient temperature, right? And then we could apply a short temperature cycle of just 24 hours, like we do it during our transformer testing, and then let it cool down and do our test, right? This would not be as severe as the proposed test by us here, but also it would help to see if during our transformer testing this bushing is okay. I mean, we are also working on another proposal where we would saturate the oil in this bushing with the help of some tubes, some hoses where we pump nitrogen into the bushing. And in this way, the saturation can be reached even faster. And I think this could be the final proposal so that we do a kind of artificial, let's say, saturation of this nitrogen, and then have a bushing which has saturated oil inside. And then we can do quickly a cool down heating first, and then a cool down test, and then prove that this bushing is free of partial discharge. Well, this is all discussions. It will be presented during the next IEEE meetings, all the details also, which we still want to do, and all the additional measurements which are doing at the moment. So with this, I think I came to the end of my presentation. I was supposed to stop at the quarter before. I hope I have achieved this. I hope you enjoyed it. Thank you for your attention, and I hope I'm waiting for your question.
Hey, thank you, Egon. Very, very good presentation. It's actually the second time I hear it, and I enjoyed it as much as the first time. I even understood it better, so thank you. There are a few questions from the attendees, but I do want to ask one or two questions first. On your slide number 12, where you have these PRPD diagrams from the low voltage bushings, do you happen to know if those were measured from the bushing tap or from a separate coupling capacitor?
Yeah, in this way, we have measured from the bushing tap. So,
okay.
So this is what we try to do in many cases, but of course, also we have the capacitor there. We can also use the calibration capacitor. It is different for different designs, but both procedures, they show us the problem very clearly, right? And the bushing was measured while it still was on the transformer, right? Which is also important to know. So when we see this partial discharge, of course, we are never sure, right? Is it the bushing or is it inside the transformer? And then normally we also look to other parameters, right? For instance, how these charges are transferred to other bushings which don't produce the problem, right? So now here we have the problems in the low voltage bushings, and then we were looking what is the partial discharge on the high voltage bushings. And then when you see that there is not nearly no transfer of energy to the high voltage bushings, then you know that the partial discharge happens in a, let's say, very well screened area, right? Which is normally inside the bushing, right? And in this way, you can get a feeling, right, where it could be, right? And also we had, maybe just because it's interesting, we had one case where we have discussed with the bushing manufacturer, and then we have put a pressure on the bushing, putting a pressure artificially, and you have to put also, or to close the bushing after the pressure is there. And then we saw that the partial discharge improves after putting the pressure, right? In this way also you quickly can see is the bushing affected. Or you open the cap as it's proposed by the bushing manufacturer, and then you see do we have a change by opening the cap of the bushing. And then, of course, you have to be sure, because the next step is then, if you don't manage to remove the partial discharge, the next step is to exchange this bushing, right? Which is very time consuming. You have to lower the oil level of the transformer, unscrew this bushing, put a new one, have a new oil filling process, and then start again with the dielectric test, right? Which is very, very time consuming, right?
Thank you. Maybe we can go to the attendee if we have time.
Sure,
ask
yeah.
one question.
Let's address the questions from the attendees. First one is interesting, I think. Which bushing manufacturer are known to not produce this phenomenon? I think, Egon, you probably have some good idea on a various factor, but probably not the vendor. But I'll let you answer that, Egon.
Yeah, I think, let's say, I don't want to really say names here in this case, so that no one feels blamed themselves, right? And what we can say is that not all bushings of a fleet of a bushing manufacturer produces this problem. Some of the bushing, they don't produce it. And then, of course, it depends on the preconditions, right? So if it's a very new bushing, which just came out of the shop, did not have long storage time, then there is not much nitrogen in the oil of this bushing, right? Then maybe the problem is not there for 100%, right? And so there are a lot of conditions which have to be considered, right? But we know that some designs, they don't produce the problem of different manufacturers. And the purpose of this test is also to first have a clear criteria to find out which bushings produce the problem. It's also maybe good for the bushing manufacturer because not all of them even know which designs produce the problem. Because of course in their test field and test area, the problem is not there, right? Because the bushing is filled with degassed oil. But the problem appears in our transformer test field, right? So therefore, bushing manufacturer may not be aware of the behavior of all of their bushings. So therefore, I think also such a test would give transparency. And probably we will not do it as a type test, but we will do it as a special test, which can be done on request. So, and probably we as a transformer manufacturer, we will request it from some of the bushings, right, to be sure that we don't have the problem.
Yeah, no, thank you, Egon. I think that's exactly why you have the proposal of this test, right, which is also part of the fact-finding process for, you know, different manufacturers, just trying to see whether there's a problem there, and then how to improve that also. So I think that's exactly why this is also raised in the standard group, with this not being a standardized test yet. So another question from the audience is, that should be quick. Please repeat how long it could take for nitrogen to create bubbles.
Yeah, so the question is also very good, right? So first of all, we need to see what is the time till we have saturated oil with nitrogen, right? And so we have seen with our test at 85 degrees that it can take, let's say, 3 weeks or so till we get a suitable level of saturation of the oil with nitrogen, right? You see here that the pressure has reduced inside the bushing and then stabilized. This is the after 3 weeks or 4 weeks. This is the time when the nitrogen is dissolved in a way that we have equilibrium and the oil is saturated with nitrogen. And then release of bubbles, you can see on the next picture, right? So when the bushing cools down, immediately then bubbles, because the pressure goes down, temperature goes down, then let's say after several hours, then the bubbles start to appear normally. And of course, it depends on the bushing design, right? But even they can still appear after 24 hours or more, right? So you cannot say 100% when they start because it depends on the design and on the preconditions. But we know that even after 24 hours, the problem is there in most of the cases. And when we have such a problem, I mean, we see it after a few hours after a cool down, because then we should test our transformer, right, do the dielectric testing. Then we see partial discharge is there. And then we open the cap to vent the bushing. And then in some cases, it reduces the partial discharge. In some, it does not disappear. And then sometimes we have to wait 2 or 3 days till the problem disappears, right? So this is, of course, also a big problem which we have. I hope this answered your question.
Thank you, Egon. Yeah, I think maybe some background also. This is also the test proposal also being triggered also on the venting procedure, right? That was the discussion back in the standard group. And the interesting part, which I found also, Egon, is that similarly on your slide 12, you know, the test is quite long. The PD test that you have running, you applied voltage for, I think, more than an hour, was it the case? And then the PD activity basically just keep developing.
Yes. Yeah, this is exactly what happens, right? Once the bubbles start to come, then they continue to come, right? And very few cases you have a kind of formation effect, right? That the bubble is absorbed and it disappears. And if no new bubbles are coming, the process can stop. But in most of the cases, once it starts, the bubbles are there. And if you keep the voltage such long time, maybe even, as I said, you start to produce additional bubbles, right? Which comes from the composition of the oil. And we know that, let's say, the hydrogen level in the oil can slightly increase also if you keep very long this voltage here and keep very long the partial discharge in the bushing, right? So you know that we can do a DGA, dissolved gas analysis of the bushings, oil. So that means we can take a sample of the oil from the head of the bushing and check the gases. And of course, we will see a high level of nitrogen because it's saturated around 80,000 ppm. But also in case, let's say, we had sustained partial discharge activity inside the bushing, then slowly small traces of hydrogen and methane can appear, right? So in this we can see that in the DGA, which was done from the bushing oil. But we did not see, let's say, after the induced testing and after partial discharge measurement, we did not see that, for instance, the very strong failure gases like acetylene are generated. But if you would not start, let's say, AC testing, right, with partial discharge monitoring right after cool down, if you would start to do lightning impulse test or switching impulse test of this transformer, then you would not know if bubbles are inside. And we know that lightning impulse and switching impulse is a more severe test than the induced test, where we just apply the voltage as is described here. And then discharges can happen inside the bushing, and we have cases where we have damaged this bushing. So, and the IEEE standard, it says that the dielectric testing should be done right away after the heating on customer request. But the normal sequence of dielectric test is that you first start with lightning impulse test and switching impulse test and then lightning impulse test. And at the end, you do an induced test with partial discharge monitoring. So, and therefore, we have introduced for ourselves to start with induced partial discharge test, right? Which is not as per standard, but we just first want to be sure there is no bubble there, which can lead to a real damage of the bushing when you do the impulse testing. Because this would be a disaster because you have then to exchange the bushing. And if you just bought 3 bushings from your bushing manufacturer, then you have to wait sometimes several weeks or months to get your new bushing, right? The replacement bushing, and you cannot test your transformer and you cannot deliver as specified, right? So therefore we have introduced this induced test with partial discharge monitoring, which we do normally before lightning or switching impulse tests, just to be sure it's free of bubbles. And then you can do safe testing. And at the end, again, this induced test to see if we produced any damage during our impulse testing.
Okay, thank you. Yeah, there are a couple of minutes left. Maybe you can address a question.
I think you can, yeah, we'll see. Sorry to keep shooting at you, Egon. I think it was a very good presentation and people are very engaged. So I think that's good. One more question is, how much impact will the rate of cooling have on bubble generation? And maybe one step further, what is the rate of cooling? What is the effect of the rate of cooling will have on the PD level observed in this case?
Yeah, so let's say it depends on the speed of cooling, right? So the bushing is on the transformer, right? The cooling happens very smoothly, so the cool down, so it takes 3 to 4 hours. Of course, this is a situation which is not as bad as you see on the right picture, right? Where, for instance, we just cooled the bushing where the time constant is very small and there is a quick cool down, right? So quick cool down is of course bad, right? So you can imagine it very well if you think about that example with sparkling water, which I told you, right? So if you have the bottle with sparkling water inside, if you open it slowly and let slowly get this pressure out, maybe less bubbles are generated, right? If you open it in a sudden, even the water can spill out sometimes, right? So the bubbles come very quickly, right? So therefore, having a long time to cool down, of course, will help that not so many bubbles are produced and not so big bubbles are produced. But what happens during transformer testing, of course, we don't control the cool down time, right? So the cooling takes 3 to 4 hours with this time constant, 3 to 4 hours, based on the design of the transformer and based on the design or the temperature, right? On the ambient temperature, right? So because you cool down from temperature to ambient. So of course, we try to avoid to have the fans switched on during the cool down so that the cool down is not so rapid. But then it's just the physics, right? So it means still then it cools down as it cools down based on the environment. And then we are supposed to start testing right after as quick as possible, right? So this means we are not supposed to wait 2 or 3 days till maybe also the bubble has disappeared, right? So therefore, we should start as quick as possible. Bubbles are in most cases generated if the bushing is prone to produce bubbles. I hope this, Mathieu, I hope this has answered your question.
Yes, absolutely. Thank you, Egon. So thanks for your presentation, Egon. Thanks for being with us. We'll move on to our next speaker. I'll let Mathieu do the introduction.
Yep, absolutely. Thanks a lot, Egon. With that, we close this, and then I understand that there are also questions on the floor that hasn't been answered, but we'll help redirecting that back to Egon as well, so don't worry too much about it. With that, here's our next speaker, John Rodgers. He graduated in 2015 with a Bachelor of Science degree in Electromechanical Engineering Technology from Vermont Technical College. He has worked for Weidmann Electrical Technology for the last 7.5 years in the electrical lab. He's responsible for a variety of low and high voltage electrical testing. A majority of it is quality testing on laminated press board for partial discharge. Please join me and welcome John. He'll be sharing the topic of laboratory consideration for partial discharge testing of laminated material. So he'll be sharing that with us. John, floor is all yours. Please go ahead and share your slides.
Hello, folks. So just a little disclaimer and intro. Unlike Egon, not only do I not speak 4 languages fluently, I don't have decades in the industry, but I look forward to sharing my very small corner of the industry and little details about how we PT test laminated material here in our lab in St. Johnsbury, Vermont. So we're going to be talking about lab considerations for PD testing of laminated material. Ooh, let's see. So we're going to talk about some basics, and then we're going to talk about how it's seen in our lab, and then we'll get into the real topic, which is kind of all of our considerations that we need to pay attention to while testing, and then we'll go to a quick conclusion. So I put basics in quotes because probably, as most of you know, I don't really consider there to be much that's basic when it comes to partial discharge. So the partial discharge patterns are based on electrical theory. Probably a lot of you are familiar with the 2017 Seagrove brochure 676, which is partial discharge in transformers. But so a lot of this information and a lot of the illustrations are from that brochure in this section, because I think they're kind of useful and they tie into how we test and why we test. So the partial discharge patterns reflect the underlying physical characteristics of specific sources, and the behavior of the PD source is strongly dependent on the PD defect. So whether it's solid, fluid, gaseous, and then also on the position of the PD source with respect to the test electrodes. So obviously the analysis of PD patterns is helpful and important for us when we test our laminated material. So again, kind of theoretically, the shape of a PD pattern is not influenced by the structure of the test object. So that is how our patterns here in the lab can look like Egon's patterns on bushings where he's testing, how they can look like patterns in an OEM test bay and things like that. And then with the increasing test voltage, the PD pattern may change because we introduce new PD events, but they're kind of hidden, or they can kind of blend in as the electrical field heightens. And then, like I said, the discharge patterns are based on theory. They're based on the physics of the discharge process. And so it's possible to define 6 typical patterns that we see, or that anybody that PD tests can see. So they are based on the material impurities and the defects, and also, again, the location, which will kind of come into play as I show a few of them. So I'm going to show the 2 most typical types that we see here in our lab. I'll give a few different examples of those so you all can see what we're dealing with. So one of the most common ones, again, from the Seeger brochure, we call it a type 5. So it would be a non-conducting material. Typically for us, it's just a cavity with no contact to the electrode. So it's kind of floating out in the material somewhere. And this is a good example kind of a single signature. So we assume that's just a single defect. As you can see by the pattern, there's kind of one single event to look at. And then we come down to our second type 5 example. And this is a good illustration of what we see and what we deal with, because at least it appears to me to be an example of some laminated material. You can see many material layers there, and that is exactly what we're testing. So this one has several different bubbles, cavities, voids, whatever you would like to call it, included in the material. And again, kind of like Egon's example of the multiple bubbles inside the bushing. If you look over to the right side, you can see an example of multiple voids. So you get multiple patterns there. And then the other one that we see sometimes is a type 4, which would be a cavity with contact to an electrode. So whether it's right close up, or I guess it would still need to be encapsulated, but it's basically in contact with the electrode on one side or the other. So now we'll get into kind of more of our real world lab examples, and we'll talk a little bit about the differences here between us and maybe testing a transformer at an OEM. So again, like we said in the first section, theoretically the shape of the pattern is not influenced by the characteristics. So that means that whether we are testing our little 25 by 50 by 10 millimeter sample, or you're testing a bushing or an entire transformer, that these PD patterns still hold true. So you can kind of determine where they're coming from. In our setting, the object is very, very simple. It's a tiny little piece of material, and then versus a several meter by several meter transformer. So it's a very different scale, and because of that, we have substantially different test criteria. So testing such a small piece of material in a controlled environment certainly has its advantages, but it also, I guess, presents a few troubles or disadvantages as well. And then obviously, if you're testing a whole transformer, there's a lot more going on, and it presents some very different challenges. But testing on an OEM floor, you may have a background noise of 10 to 50 picocoulombs, and then based on testing standards, acceptance criteria may be 200 to 500 picocoulombs. But for us in the lab, our background is typically less than 1 picocoulomb, and acceptance criteria for testing our laminated samples is typically between 2.5 to 3 picocoulombs, which is pretty darn low. Oops. So here is kind of a snapshot of our lab and our test setup for testing laminated material. Typically, our inception voltage or inception PD level is based on the current background. It stays pretty consistent, so typically it's right, like I said, it's right around the 2.5, 2.6, 2.7 picocoulomb mark. And obviously, we're here at the OMICRON event, and I would just like to say that the MPD system has enabled us to have a much lower background noise and also higher testing precision. Just, you know, I think it's mostly due to the components. It has the battery power source, it has the fiber optics, so it's way ahead of the game from the unit we used to have. And so we get a lot better test results and precision from that. So here is a PRPD snapshot from our lab. So to the best of my knowledge and abilities, I would conclude that this was kind of a multi-cavity example. So we have some air bubbles either in the glue line of the material or the glue zone, which is kind of like splitting hairs in our material, but there's kind of a few different areas of the material that these kind of things can happen. So again, if you look down towards the bottom, our background was around 0.8 picocoulombs, and the peak of the event was 30 to 35 picocoulombs. So it was substantially above our background noise. And then here's another, this is kind of as basic as it gets, another type 5. So we assume it was another cavity in the material, and you've got the nice kind of typical shape of some sort of cavity air bubble. So, and then I think we have a couple more examples. So this is kind of a nice one that we assume to be some sort of conductive material inside our test sample. You get a nice straight line across for that kind of thing. And then we can also see that there's probably a void as well, but you can see it's kind of superimposed inside it, but you can see it underneath it. So we assume that there was at least a metal particle and maybe even a void in this one. And then I like to kind of give an example of some corona discharge. So it's similar to a type 1, but it's a conducting material with contact to electrodes. So quite often if we see something like this, and obviously I hooked a corona wire there so that we could see it very nicely, but if we see something that's one-sided and looks similar to this, then it's usually a good indicator that there's something not right in our test setup. There's something protruding, or even a bad connection that is arcing or something like that. And I like to say a lot of times with corona that if you can hear it or smell it, then it's bad news. So you got to do something about it. So when we test our laminated material, the obvious question and the question that you try to answer when you're doing most quality control stuff is, are there flaws or are there issues with the material? And it's most common in our material to see issues with the glue line or in the glue zone, just because that's where a non-press board material is introduced, and then it affects the material on either side of the glue line. So, and the other thing that we like to keep track of and try to avoid is any sort of contaminant. So whether that is water or carbon or metal flakes from some aspect of the you know, the sample prep procedure or the test procedure. Those are things that are obviously important to avoid, because when you have contaminants that cause PD, you're no longer looking at the PD in your sample. You're getting false results that you don't want. And the biggest thing to consider when looking at the results for us is that PD inception detects flaws that we wouldn't otherwise be able to see. You know, this is on the microscopic scale. You know, air inclusions that are, you know, fractions of a millimeter in size. So it's not like you can pick up a chunk of laminated press board and look at it and say, oh yeah, there's air bubbles in this. We got a problem. It allows us to see things that we otherwise couldn't. And the PD value obviously indicates that there is a flaw. And then to go a step further, based on the patterns that we see and record, we are able to maybe not with 100% certainty know what's going on, but it at least enables us to hypothesize about what's going on based on whether it's you know, voids, multiple voids. If we have a metal particle, then that's maybe some issue with you know, the process getting contaminated. So it helps us identify those things. And with the sensitivity of our equipment and the fact that we have a very small sample, we like to get everything as perfect as we can, because on that scale, every tiny little influence can be, you know, detrimental to getting good test results. So again, our failure criteria is less than 3 picocoulombs, which is you know, that's pretty small. It's pretty small value to try to keep track of. So you can't be inducing PD that you don't want. And so yeah, let's talk a little bit about how we make that happen here in the lab. So our testing considerations, again, you know, we have about a 11 cubic centimeter sample, and we like to think it's a very controlled lab setting, but there's still a lot of variables that need to be considered. So one of the I guess big things is the entire chain, I guess you could call it, of the testing process. So that starts, you know, from the input power to the system. Is our transformer free of PD? Is our bushing free of PD? Is the connecting tube free of PD? And on and on and on, all through the test, you know, fixturing, then through the sample, then out the other end of the fixturing, and then all the way down until earth ground is made. So there's a lot of little intricacies and parts and pieces that can go wrong when you're looking at that. So I'm going to talk about kind of the 6 big ones for us that affect reliability and accuracy. So we'll talk about sample prep and handling, then our partial discharge background levels in the lab, and then outside influences, which are, you know, that's not just the us thing. That's kind of whenever you're testing PD anywhere, there can be outside influences that you need to deal with. And then, as I mentioned, we'll talk about fixturing and then calibration. So when we are prepping samples, we've kind of developed this as the years have gone on. I think when I first started in the lab, we may have just been cutting samples with a chop saw. So at this point, we cut the sample blanks to approximate size with a chop saw, and then we mill both sides with a big end mill to get it, you know, as close to perfect as we can surface wise. And then we go a step further and we use a Dremel. We go around the edges and make sure there's no you know, fibrous burrs or anything hanging out, because when you're trying to sit, you know, perfectly between two electrodes, you want the surfaces to be, you know, flat and parallel, but you also don't want there to be large ridges and imperfections in the sample surface, because you know, in theory, you could induce PD that way if there's air there or something weird going on there. So we try to be very careful about the finished surfaces of our samples. And the other thing that's super important is that we dry and impregnate based on an IEC standard, which dictates dry out time in an air oven, and then time under vacuum and things of that nature. So one of the big factors of that process is keeping the moisture low. So the sample itself, the laminated sample itself, is typically around 0.3% moisture. It's always less than 0.5% moisture to be tested. And the other factor for that process is to make sure that the sample is as impregnated with oil as it can be. Again, if you don't have things properly impregnated, then there's the possibility of even more air voids, cavities, than if it was impregnated. So that's important as well, to having as clean of a sample PD wise as possible. And then for sample handling, the sample remains under oil at all times once it's impregnated. So we are careful we don't, you know, take the vessel and dump it in the test tank. We don't reach in and grab them and drop them in, because it allows we don't want to allow the sample contact with ambient conditions. We don't want to include any air potentially that would otherwise be avoided. So we're very careful. We impregnate under oil. We set them into the test tank under oil, and excuse me, keep them covered up well. And once they're in our test vessel, the oil is continuously processed. So that does a few things. It keeps the oil free if there are breakdowns during testing. It keeps the oil free of carbon, which can cause issues. And then it also keeps the oil dry. So, you know, in the humid summer months, it's a little more of a struggle, but we always test below 10 ppm of moisture. And typically it's 3 to 5 ppm throughout the day when we continuously process. And then if the samples are not inside the test vessel, they remain in a vacuum oven, and we make sure that they are under oil and that they also have a dry nitrogen headspace, again, to try to keep any unwanted moisture out. And then we also want to make sure that when we're handling them, we have pliers and gloves and such like that, but we want to make sure that everything is free of carbon and other contaminants. So background PD levels are obviously a large factor when testing, because when you're measuring at 3 picocoulombs, you can't measure that if everything is lost in noise. Like I had mentioned before, typically our noise floor is between 0.7 and 0.8 picocoulombs, and that has significantly improved now that we have the MPD system. Our old system, we kind of bounce between 1 and 1.2, sometimes 1.5 picocoulombs, which again makes getting good, accurate results difficult. So, and then we come to outside influences. So I like to say the cleanliness of the lab is important. We want to make sure that you know, we reduce the amount of objects that are close by, any sort of metal objects that, you know, could have partial discharge. If they were close enough to have some induced voltages or anything like that, we want to make sure that's taken care of. So we kind of space everything out. We make sure that the Marks generator over the right side is grounded. We have a capacitor in the back that's off against the wall and grounded. We just want to take care of all those things to make sure we're not inducing some, PD around the lab. Another factor that comes into play because, outside the lab is the shop floor. So we have a lot of manufacturing processes going on out there, and they also sometimes do maintenance related things. So whether they're working on a motor or doing some welding, in the past we've had kind of weird PD events that we couldn't explain, and we kind of talk to the maintenance crew, and they say, oh yeah, we were out on the shop floor welding, and it seems like we can see those kind of things. So if you're seeing PD oddities, sometimes it's a little bit beyond your control, unfortunately, but all things to consider. And then funny enough, the lighting and the ballasts in the lab. So as you can see in the picture, there are the kind of standard fluorescent fixtures up on the ceiling, the 2x4s. So we can't run those when we test. The PRPD file screenshot there is from the lab when those fluorescent lights are on. So obviously we aren't able to test, at 1 or 2 picocoulombs if that looks like 7.8 picocoulombs of noise. So we have the kind of accessory LED lighting that we turn on when we PD test, and those are nice and quiet, unless one of them is burning out, which we've seen. Again, you see a weird PD signature, and you kind of start chasing your tail around saying, what could be going on? And you start flicking switches and looking at stuff like that. So yeah, just the intricacies and oddities of PD testing in the lab. And one of the other kind of interesting oddity outside influences that I wanted to touch on, again, just because it's one of those things that until you see it and do some digging, you really don't know exactly what's going on. So we have a large overhead door that goes out to our shop floor, and partially because of the increased sensitivity of the OMICRON unit, we were able to kind of pick up on it. So we noticed that a little bit of noise that you can see over on the right side corresponded to actually being able to hear the door rattling. And it was something we didn't really see with our old system just because we didn't have the sensitivity. But it's all about if they open up other exterior doors out on the shop floor, there's a pressure change and we get a rattle on the door. And we could see it on our PD monitor. So that's something that we had to kind of figure out how to avoid. So there's the culprit, our large steel overhead door. And we kind of found out that to get that door to quiet down, we would stick a piece of angle iron inside between the door frame and the actual door. It prevented it from rattling, and thus we don't have that kind of weird intermittent noise anymore. So it's just kind of a fun little example of how it takes something very simple and seemingly unimportant that can go wrong and kind of play with your results and make you scratch your head. Another important factor, or factors, because it's got a lot of parts and pieces, but the fixturing kind of inside and outside of the test tank. So one big thing is to have good solid connections, whether it's out in the air or in the oil. If you have poor connections, you can 100% introduce some PD into your system. You see that we utilize a lot of spheres and toroids. That kind of reduces localized stresses, gets rid of sharp edges, and again, helps us hopefully cut back on unwanted PD. We have the bushing, a large porcelain bushing that goes down through and breaks the oil surface. And then another factor that we always consider is our electrodes. So not just the profile, as you can see in the lower left, we use Rogowski profile electrodes, which have a nice radius so that there aren't sharp edges that close to the test sample. And then we also want to make sure that they are clean, so free of carbon from other testing, and also that the surface is smooth. Again, kind of, it wouldn't do much good to have a nice smooth sample surface if the surface of the electrode isn't also nice and smooth. So we do surface electrode maintenance, fairly regularly. So calibration, very important step of all this. It's I don't know, you can throw the longest shot put if your measuring tape isn't right. So we calibrate at least once per test series. Usually we do it every morning, just as a rule of thumb. But we calibrate to between 50% and 200% of our testing limit, because that's what the IEC standard kind of dictates. So like I said earlier, our limit is around 3 picocoulombs. We calibrate at 5 picocoulombs. But it's just, again, it's important to know that all your settings and calibration is right so that your numbers results are meaningful. All right, wow, to the conclusion already. So lab considerations, test process, all that things. Why is it important to us? So again, these considerations and kind of going down through the checklist, making sure that all our ducks in a row, they allow us to measure at what we consider pretty low levels. Visual or mechanical testing of laminated material is useful for other parameters, but it's not a good way to decide if your laminated material is of adequate quality for dielectric strength. PD testing is truly the only means that we have to identify flaws and therefore make conclusions about the material quality. And then recognizing the patterns, and then to go a step further, the associated breakdowns is beneficial and important to us. A few types of the PRPD patterns can kind of represent contamination issues, whether, again, that's water, carbon, metal, whether that comes from us or production. That's helpful to know. And then type 5 can represent issues with the gluing process or even the base material, whether the glue is too thick or not thick enough, whether they put too much or too little on, whether they pressed it too hard, too soft. And then it can go a step further to the base material. If it's, if the material's too free or not free enough and it's not absorbing the right amount of oil, things like that. And then Corona is fairly easy. That one can help us identify issues with our test setup. The PD results can also help on the customer end differentiate between material qualities. So there is no specific PD inception criteria in the IEC standard, but we here at Weidmann have our own laminated pressboard specification that does include a pass or fail based on the PD levels of the testing. So a few things that I think I would like you all to take away. So to go way back to the beginning and some of the basics, in theory, the PD pattern is not influenced by the structure of the test object. So that means whether it's our tiny little sample here in the lab, a bushing cable or a full transformer, that these patterns, you know, hold true, and that the complexity, material type, etc., doesn't implicitly affect that pattern. Recognizing the patterns aids us in recognizing potential material issues, again, contaminants, process issues, anything of that sort. That's why we're doing it. And you cannot have accurate partial discharge data, especially when it comes to in our lab environment, without clean samples and setup, so that you know that you're not creating PD that isn't supposed to be there. You can't have accurate data without a low background that enables you to properly measure the levels that you want to measure. You also can't have accurate data with a lot of noise going on. Again, sample issues would get lost in that noise, so it's important to have as low noise of a environment as you can, and then proper calibration. You can't measure 3 picocoulombs if your system isn't actually set up to measure that level. So when we deal with all of these intricacies and factors, that's how we know that we can get reliable and accurate data, which then, you know, helps us determine that we're doing something right or wrong with our process, and also allows, you know, the sales team and beyond customers to know that they're gonna get a product that has the appropriate partial discharge levels and dielectric strength and everything that makes everybody happy when they're paying for a product. So yeah, I guess that is the end of what I have prepared.
All right, thank you very much, John. For those of you that joined us the first time, John is actually a return speaker. So again, thank you, John, for supporting our event. He presented in the Symposium 2 years ago already, and I always found it interesting because it's a very different topic. It's sort of uncover, you know, the mystery of, you know, on more on the material component level that we usually don't see, you know, after the asset has all been assembled, right? And John actually brought us sort of through the journey of building a testing database, measurement technique, you know, talking about some tips and tricks as well. So I think that is always beneficial. Let's address some of the question on the floor. Let's go with the first one. So if you have PD in the laminated material, what is the consequences? Would it lead to failure? You know, how does the study show? How long before failure? Multiple questions, right? I think, John, you can also see it on your end.
Yep.
And maybe some comment from you?
So it's difficult to say with certainty yes or no. Obviously, we wouldn't be doing the testing if we didn't think that the data was valuable and the results were meaningful. But we, like I showed you, whoops, let's see. Sorry, that's our test sample, right? And we test 15 of those per sheet. And I want to say the sheet of material is 6 or 7 feet wide, 8 or 10 feet long, and then we get little sections of it cut out that we test. So the consequences in theory are, if you have material that you test 15 samples from and the PD results are bad, the thought is that that load of material maybe has some issues, and that could, in theory, lead to a failure. Now, obviously, there's a lot of variables, right? Because each, you know, you're testing very small sections of a sheet. There's multiple batches of that material made in one test run. There's 2 or 3 loads made a day, and et cetera, et cetera. So it's not 100% a guarantee that you know, if we see partial discharge in one sample per load, that that the whole load's bad and that it's going to lead to a failure if we send it out. But we do have practices in place that if the PD results are not up to our standard, then that material gets allocated for something else. So that material does not go to market as material to be sold for a certain dielectric criteria, you know. So I guess, and what, let's see, do you expect it to be free? Is that such a thing for this material? I wouldn't say that the material, well, yeah, I guess it could be considered PD free, but again, we test to a certain level, and if it passes that, then it's considered PD free to a industry standard. But I think you could probably create PD at a certain level. You know, if you're testing far above the standard or the criteria that maybe you would see PD. Yeah, and as far as how long before the failure, that's a good question. I mean, yeah, I'm not sure. I won't answer that because I'm not. I'm just a lab tech and engineer on this end.
Thanks a lot, John. Well, I think one thing that you're really addressing it right is, you know, as long as you keep increasing the voltage, certainly at some point there will be PD. But I think real well answered. Essentially, I think that answer also the second part of the questions, which is good. But yeah, a lot of things that you do, I think, is really on the quality control side of you know, the production also. So I think that sort of answered the second question. Mathieu, to you, would you like to address some of the question here as well?
Hey, thanks, John, for the presentation. It was very good again. Yeah, maybe I can circle back to the last question. I mean, when you're testing your, I guess the voltage level at which you're testing your sample, I guess will provide an electric stress which is higher than what will be seen in operation anyway. So basically, if it's PD free in your condition, it should be PD free as well inside the transformer at the operating voltage. I guess that's the main goal of all that. I was curious to know if you do some sort of I'll say voltage endurance testing, or do you do thermal cycling as well on your sample?
Yeah, so we don't do any sort of long-term voltage tests, but we do a few different thermal tests, you know. So, but not dielectrically, I guess. We do it on the mechanical end of things. So we age our samples at an elevated temperature for a week or two, and then we do mechanical tests. But actually, it's something I was chatting with somebody about recently. But no, we've never done any sort of dielectric testing with laminated material that has been aged at an elevated temperature. I think it would be very interesting. But no, that's not part of our standard procedure, or really anything that I've seen in my 7.5 years either.
Perfect. No, I think that could be interesting. I know it's done for other things, just to see, for example, when that material expand, right? It's a milled layer material, so maybe they don't expand at the same rate, and you can have shears between material created. So yeah, I was just curious. And have you ever performed, that's related to a previous question we had. When you have PD or voids inside one of your material, have you ever used X-ray imaging to try to locate those voids, to have a view of?
Yeah, so sometimes if we have a sample that has a very distinct and interesting PD pattern, and maybe it was a cause for the load or batch to fail, whatever you want to call it. Sometimes we will attempt to see things with an X-ray. With that said, a lot of these voids, inclusions, whatever you would like to call it, are very small. So sometimes it's tough to see or even determine where it is. But we do have some sort of high-tech CT imaging over in Switzerland, and we're kind of working. A large group of us at the company are working on a PD in laminated material project, trying to really dive deep, figure out some of the causes for these phenomenons. And that will be one part of the project, is to take, small pieces of our material and do very, very, very fine, in-depth CT scans to try to see if we can actually see these defects or not. But it's pretty difficult at this point to try to see them.
Perfect. Awesome. No, that sounds interesting. I guess we might see you again in the symposium at some point with more with some results.
Right.
Thank you, John. Thanks for the presentation.
Yeah, thank you guys. That's great.
All right, thanks a lot, John. I think with that, we are right on time. We'll move on with our next speaker. So our next speaker is William Larzelere. So Bill, thanks for joining us. Bill began his high voltage career as a design engineer at Habertronics Inc. after achieving a Bachelor of Science degree in electrical engineering from Union College in the state of New York. After holding many engineering positions in Habertronics, he was an officer and board member of the public company until it was later acquired by Hubble Inc. Bill was the long-time chair of IEEE subcommittee on high voltage testing techniques. He has been a member of IEEE insulated conductors committee, IEEE transformer committees, U.S. member of C-grade D1, and U.S. technical advisor to TC42 high voltage testing techniques for over 30 years. He is the author of numerous peer-reviewed papers on high voltage testing and has contributed to a lot of IEEE, IEC, and C-grade guide and standard. Currently, Bill is president of Evergreen High Voltage LLC, a supplier of high voltage test instruments. Today, Bill will be sharing with us the high voltage partial discharge filters for field and factory testing. Bill, it's great to have you here, and the floor is all yours. Please go right ahead.
Good afternoon, everyone. Thank you for your attention. I'd like to talk a little bit about some solutions to getting better sensitivity in PD measurements. Previous authors have talked about some of these issues, and particularly background noise levels. And we also have partial discharges coming from sources. And so this presentation, if I can get this going here, clicking on, trying to start. Am I clicking on the wrong place?
So you'll click on the presentation and do page up, page down buttons.
Okay, so here we go. So the problem that I wanted to talk about a little bit in terms of a solution is, first of all, where are these noise sources coming from? And in the factory, when we're doing partial discharge testing, we're normally in a shielded test environment. That could be a Faraday cage, or it could just be a dedicated laboratory. But the bottom line is that we need a signal to noise ratio of 2 to 1, according to IEC 270, which means that the noise has to be significantly smaller than what we're trying to measure. So it's not masking the actual partial discharge. We have to remember also, I think, that we're measuring the apparent charge. We're not actually measuring the discharge here. So when we measure the apparent charge, our system really is a quasi measurement system. You cannot actually get inside, say, John's piece of insulation and actually measure the charge or discharge from a particularly bad source of inclusion or whatever it may be. So the external conditions that surround a partial discharge test have a lot to do with what we could actually measure, and therefore how we can interpret what that really means. So we have a lot of digital filtering possibilities that have come from the last 20 years or so. Now that we've digitized these signals that we're getting, these apparent charge signals, and there's a lot that can be done on various noise sources, but there are still some nasty noise sources that we can do very little about. So today, what I want to talk about mostly are the conducted PD noise sources, which come from whatever high voltage equipment you're using to generate the test voltage. So when we talk about radiated PD noise in the environment, you know, we've got lots of nasty things out there, rotating machines, power electronics these days, lighting sources. There are all kinds of different air connected by capacitive coupling sources that interfere with our measurement system. Some of these things are fixed, which is nice because then we can identify them, we can see what they are, and sometimes window them out, or at least recognize them as long as they're not masking what we're actually looking for. Faraday cages, of course, in the field are not very practical because we're in a substation. We've got all kinds of air insulated equipment around us, switching devices. We also have ground induced noise, and this can be a problem in a factory or in the field where we have large conductors buried in the ground that are returning current, and there can be significant noise generated into our ground system, which we think is quiet and stable. But a lot of times, even in a factory, it's not. So when we talk about directly coupled PD noise on our test terminals, the output terminals of our test device, you know, we've got mains coupled noise from the source of power, wherever you're getting that from. We've got the controls for the test source that may have frequency converters or switching devices, even electromechanical relays that can cause splatter that will be showed up on the screen. We have voltage regulation devices. They're electronic or mechanical voltage regulation devices that can cause noise. Comes right through our test system. And then, of course, in the high voltage source, it's a transformer, a reactor, or whatever it may be, there can be internal PD from the insulation, from the connections, output cables, anything to do with the high voltage source itself can be a source of background noise that is the threshold to have to look through. So as I said before, the PD display patterns can show you what some of these sources could be. There's some automatic software that can help you with that too. But again, if the level's high, it's going to be a problem in terms of actually making a good measurement. And I said, this windowing option is nice for fixed sources, but again, you have to be very careful that it's not going to occur where your PD noise actually is as well. So if you look at a basic source, here's a test source. It could be a AC transformer, it could be a series resonant system, parallel resonant system, VLF, could be a wide range of different sources, and you've got possibility of PD noise coming in on the mains. It's going to get through in some way, shape, or form. Could have radiated PD in the test area, radio frequency stuff that's directly coupled to your output. Or you can have this ground-induced business that I just mentioned. So for the line conducted noise, we have transient and we have steady state noise. So different sources could be tap switches, electronic converters, motor controls, vacuum switchgear is particularly nasty because it sets up traveling waves, particularly in high voltage cables that can run around. We have the discharges in the insulation in the source itself. So again, we can put a line filter to knock down some of the line conducted noise. But one of the problems with line filters is that they're usually designed for radio frequencies and not down at the lower frequency level where most of these noise sources come from. Typically, this would be under 100 kilohertz. So here we see a typical low voltage filter. We've got the mains, we've got an AC source, and again, we've got a filter before the power actually gets connected to our test set. Excuse me. So the internal control PD sources, modern controls are filled with electronics, especially where we have motor controls in large test systems. These can produce a significant amount of conducted noise that comes right through and appear on the output terminals of the test source. So there are a variety of these different types of devices, which you can see I've listed here. And again, some of these things are nice. They're fixed amplitude and we can identify them clearly, and some of them are not. They vary and they become very difficult to find or to filter. So again, we've got our filtered mains, then we've got PD in our control system, and there are a wide range of control electronic filtering devices that we can use. Some are effective, some are not so effective, particularly in the band where we're working. Then we come to the high voltage. The source is a complex little box. It's got insulation structure, there are windings, there's some of Weidmann's very nice insulation inside. We have terminals, bushings. We have all these different components, and all of them can create partial discharges. Again, some are easy to identify and some are not. Some are fixed and some are random. So we have a variety of options here in terms of what can be causing our trouble. So what do? We've got a test. We're going to try to test it. 3 picocoulombs is our pass-fail criterion. We're looking for 1.5 PC of background, including all components. That means the high voltage source at that test voltage has to have less than 1.5 PC. So what do? Of course, we can do some digital signal processing. We can identify some things and reduce them digitally. We can improve the shielding in the test environment, which is pretty difficult to do in the field. We can eliminate air terminals by using cables and plug-in connections to our test object to reduce radiated couple noise. The mains noise, we can deal with that. Just a slight digression here. Conventional mains filters that you can buy from radio frequency guys hardly do anything below 100 kilohertz. And the majority of the noise that comes with AC power frequency or even VLF test sources is below 100 kilohertz. So line noise that's in the lower frequency range requires special filters if you want to do something about that. Anyway, just to move on to the high voltage side, once we've got noise coming through our high voltage source, we need a high voltage filter, and that's what we're going to talk about now. So if you look at what a typical high voltage filter looks like, we've got an inductor, we've got a filter capacitor, works as a nice little voltage divider. Perfect inductor, perfect capacitor gives us wide bandwidth, and we can, so if we made pure inductors and pure capacitors, we could make pure filters, and we could eliminate with a high degree of attenuation partial discharge signals that are coming from the terminals of the high voltage source. This is a typical example of what a high voltage filter would look like. In this case, it's a 35 kV device, good for up to 8 amps. This is for power frequency testing. So you can see the filter is in series with a capacitor. The connection's made at the top and at the top terminal of the capacitor to go to the load. So we have an inductor in series with a capacitor connected to a load. We have a lot of different kinds of test voltage sources. We have transformers, which couple PD noise through them quite well. We have parallel resonance systems, which are basically a transformer with an inductor in parallel. Similarly, the partial discharge can pass through that configuration pretty easily. We have variable inductance and variable frequency resonance sources, which give us some filtering. If we look at these schematics here, on the top, you can see the series resonant configuration where basically you have a transformer and then you have an inductance in series with a load. So that inductance acts as somewhat of a filter, depending on its design. If you look down at the other configurations at the bottom two, where we have a parallel resonant and a regular transformer, basically you've got a galvanic connection directly from the transformer that's in that source to the load. So we also have VLF sources, and we have different designs of VLF sources. We have electromechanical designs, electronic designs, and we have oscillating resonance sources too, which have electronic switching. So we have a variety of test voltage sources, all of which to some degree can create partial discharges on their output terminals, which then are connected to your load that you're trying to test. So the typical high voltage filters, as I mentioned before, we have a high voltage capacitor with very low inductance, and we have a blocking inductor with very low capacitance. So these devices can be cascaded, or they can be as a single filter, depending on how much attenuation is required. And then the component design depends on the frequency range that we're trying to address. So we also have the consideration, we have an inductor in the filter. So we have a voltage drop across that inductor we have to consider. And then we have a capacitor and we have a test source with a limited capacity. So we have to think about how much current that capacitor is going to draw. So we have several criterion to determine how we design the filter. Not the least of which is how much PD you have in the source. So unfortunately, what happens when we try to design these big components, these are large physical components, is that the inductor ends up having stray capacitance and the filter capacitor ends up having stray inductance. So depending on how we design those components, they will either act as a nice stable inductor or capacitor or have poor frequency characteristics as we go up in the higher frequency ranges, particularly in the PD measurement band. So here you can see two different configurations. I showed a picture before of a typical AC filter. The AC filter is on the left. It's got a single inductor. We're talking about relatively high currents in this configuration because if we're testing medium voltage cables in the field, typically we're going to be drawing a reasonable amount of current. So we have pretty good sized wire on the design of those inductors. The VLF style filter, the current's much, much lower, the frequency is lower, and therefore we can use smaller wire and we can go to higher inductance values. And so we use more of a pi style high voltage filter. There are some other things that are involved in these filter designs. We can have flashovers of the test circuit when the cables are being tested, or the switchgear, or whatever it might be. And that flashover will impose a very high rate of voltage collapse across the high voltage inductor. So we have to be very careful to protect for that. Otherwise, we can fail the inductor. So I mentioned a little bit about idealized components, but so if we had a perfect inductor, its reactance, its inductive reactance, could be calculated based on the frequency, very simple. And same for the capacitor. So then, we would have a attenuation ratio, or voltage in over voltage out, based on the angular frequency and the component values. So we design the filter, we size them for the loading of our source. Everything is perfect, and we get the attenuation we want based on how much noise we want to knock down that's coming from that test source. So the basic relationship is this. We have a voltage of the partial discharge event, and we have it developed across the filter. And then on the output terminals, we have the reduced value of that V1. Unfortunately, in the real world, we have to make these large components. And for inductors, we have stray capacitance between the turns. We have many turns in these inductors. Then we have layers in the windings of the big ones. So we have stray capacitance between the layers. So those stray capacitance determine the self-resonant frequency of that inductor. And then above that self-resonant frequency, the inductor is no longer a filter, it's acting as a capacitor. So if we want to have an inductor that's going to work at least up to a megahertz, we have to have a self-resonant frequency in that range. Here you can see schematically what I'm talking about. We've got an inductor, which is a series of turns on a winding form. We have capacitance between the end terminals and, of course, between the individual turns and the layers. High voltage capacitors also present a similar problem. We have finite size. So these capacitors are pretty big, so they physically have an inductance based on their size. And we have to have a certain height of these capacitors because they have a certain voltage rating. The higher the voltage, the taller the capacitor. So the minimum inductance that we can get in a high voltage capacitor depends on quite a few things, actually. The winding technique inside the individual sections of a capacitor have a main determination of what the inductance of that capacitor will be. Quite a few years ago, there was research done to come up with a method for minimizing the inductance of a high voltage capacitor. This was done in the plasma physics world. And what we have now in the high voltage world is the ability to use that technology to make very, very low inductance capacitors so that we can get the self-resonant frequency well above 500 kilohertz, even in 3, 4, 500 kV capacitors. So for these capacitors that we're talking about today in the testing range of 35 kV class insulation, let's say, we have the ability to make quite a good capacitor that will do a good job for us with a high self-resonant frequency. Here you can see typical versions of them. The one on the left can see that we've also isolated the base of that capacitor. When we make multi-stage filters, oftentimes we may want to put an MPD quadrupole on the base, so we isolate the base so that we can actually measure voltage and PD from one of the stages of one of the filters. That's more or less a standard design now. So again, if we talk about how to size the inductors, what we're looking for typically is about a 2% maximum voltage drop. So in the case of power frequency, field testing, typically here we're talking about cables, we're talking about higher current loads. So we're up to 10 amps in many cases. So that limits our voltage drop based on current and therefore the inductance of the filter inductor itself. For VLF systems, the currents are lower, so the inductors can be much higher L value. And however, we still have to wind these things and we have to deal with the self-resonant frequency issues, so it becomes a good filter for regular IEC 60270 PD measurements, and that complicates the winding design to keep the stray capacitance low. So what we end up with for power frequency, and when I say power frequency, this is to include variable frequency testing in the field. So we have a range from 20 hertz to 80 hertz, more or less. Currents, can be in the 1 to 10 amp range. So that comes out with 100 to 500 millihenries would be a typical inductance value for the high voltage filter. For VLF, we have the ability to go to much, much higher values. However, the physical considerations, winding considerations, limit us to about 1,000 henries for a typical VLF filter. Capacitor sizing, again, we're looking at limiting the current draw from our test source. So that also plays into a physical size of the capacitor that's practical for use in the field. So we have a pair of criteria here that weigh in on what capacitance value we pick for the filter. We also have the issue of the stored energy in that capacitor, and if there's a short circuit in the test sample, that capacitor will be discharged into that test sample. That may be good, that may not be good, but this is another criterion that we have to consider. So for power frequency, again, we're looking at that range from 20 to 80 hertz. Typical capacitance values are 10 to 50 nanofarad. Now, there's another issue here that we have to think about, and that is what coupling capacitor is going to be used in the circuit for measuring the partial discharge. So if we're testing very, very light loads, small capacitance values, switchgear, let's say, typically we would have a 1 nanofarad coupling capacitor because the capacitance of the test object is very, very small. But if we're testing 500 meters of 35 kV class cable, then we want to have a bigger coupling capacitor so that we can get better sensitivity of the partial discharge measurement. So these things all come into play, particularly when we're talking about multiple stage filters. Because the gain, if we're going to test a very long run of cable in the field, the gain of the amplifier and the PD detector is going to be cranked up. So we want to try to have more filtering if there is partial discharge in the source. So this is sort of a juggling act depending on the application. So we really have to pay attention to what we're testing to design the optimal filter for that application. And of course, it all starts with knowing what the partial discharge noise levels are from the test source. So it's more or less in a range of production, but it does depend on the application, how we optimize the filter characteristics. Back to VLF filter sizes. Now we could, again, go to much larger values. However, again, we've got physical limitations, and then we've also got a stored energy issue as well. So we typically keep the range in the 10 to 50 nanofarad region. So again, the problems in the filter design is we have components that are not perfect components. And we also have to be aware of A, the source, and B, the load. So the load has its own characteristics. It has its own characteristic impedance. This impacts, to some degree, the filter characteristics. So we have to look at this from a holistic standpoint as opposed to a one-size-fits-all. This is an example of recent production. It's a 50 nanofarad capacitor with a 100 millihenry inductor. That's the nominal value of the inductance, which would be measured with a typical RLC bridge. The resonant frequency is, determining the filter characteristics. So here you can see, if we calculate a 10 kilohertz, which is where, in this case, this particular system had its worst noise contribution. The calculated attenuation for those values is about 18 to 1, but the actual attenuation at 10 kilohertz is about 15 to 1. If we go up to 100 kilohertz, it's more like 10 to 1. So the parasitic inductance and stray capacitance of the components gives us a frequency characteristic that's not flat and rolls off with higher frequency. However, 10 to 1 reduction, if the source has got 10 PC of background noise, takes us down to 1, so we're in business. So again, depending on what we're trying to do here and what the source gives us, that tells us what we have to do in the filtering section. So, and again, what we've done in many cases is we've had 1, 2, or 3 filters in cascade where we've had particularly nasty noise sources, or we've had very low capacitance test loads, which required the amplifier gain to be set very high. That's a typical example. Here you can see that 3 cascade setup. So VLF is a little bit different. We've got different inductances, different inductor design, similar capacitor design, but the calculated attenuation you can see is 180 to 1, 10 kilohertz, and then 10 kilohertz. An actual attenuation is more like 100 to 1. So it's still rolling off, but due to the design of the VLF filter, we're actually getting more bang for the buck in terms of a physical size that we can fit on top of the filter capacitor and still be manageable as something that can be taken in the field. So to conclude this, what I've tried to explain is that if you have a perfect source, of course, you don't need any filtering. But in 50 years of doing this business, I have yet to see a perfect source, particularly a perfect source when we're testing a large capacitive load. As the gain is cranked up, then the background noise level goes up too. So what we've been able to do is we've been able to create high voltage filters that can bring the background noise level down to the point where our sensitivity for the actual measurement allows us to get the results that we need, whether that's 2 PC or 5 PC or 50 PC. I think now the standard for cables in the field is all 2 for very special priority cables. I think the measurement levels are somewhat higher depending on what the cable is installed for. But in order to achieve those kind of results, these filters have been very helpful in allowing us to make these kind of measurements. So if anyone has any questions, you can contact me through this webinar or contact me at any other time. So I thank you very much.
Thank you, Bill, for the excellent presentation. This is a topic, at least, that me and Mathieu encounter constantly for both factory and field testing. I do have a few questions regarding the filters, mainly the inductors. So what we encounter, and that's for cables mainly, is that the filter we see in factories or even in the field do quite a decent job in the IC range, but then when we increase the frequencies a little bit in the lower megahertz range, we start to have issue because of the strict capacitance you talked about for the reactor. The reasons for that is that the localization is done at higher frequencies. What is a solution in your design, or what is a common solution that filter manufacturer can take to improve that, if that's not something that is proprietary?
Yeah, yes, I mean, that's a subject of research right now for sure, because we've run into this problem, and we do have users that want to go to higher bandwidths, wider bandwidths, and higher frequencies. And we're running into a problem with the physical size. So there are some technologies that we're experimenting right now with to get the self-resonant frequency of the inductors higher. And I can only say right now that it's inconclusive as to what the results are going to be. But this is definitely something that we're having requests for more and more.
Thank you. And maybe one more question. So someone that tests cables or even generators going to see quite a wide range of capacitance for their test object. Will the filtering capability of a filter be affected by the load, the current that's going to go flowing through it, or not that much?
Well, I think it's definitely the characteristic impedance of the load has a direct impact on the filter effectiveness. So if you connect, a load with a very, very low characteristic impedance, you're going to have a different filtering effect. So again, it's a family of calculations that you would have to make, and you would have to know those characteristics, but definitely there is an impact. I think one of the ways to mitigate that impact with lower impedance is to go to multiple stages of filtering. And that's exactly what we've done. And that has allowed us to be able to test those more difficult cables and get reasonable sensitivity. But there is no doubt it's a 4-terminal device, and the characteristic impedance of the load is going to affect the filtering effectiveness.
Awesome. Thank you, Bill. I don't see other questions from the participant. Do you have any other comments, questions, Mathieu, or?
No, I think we are actually quite on time also. In general, I think we can go for a lunch break, and then come back. But thank you very much again, Bill. This is certainly a complex topic. I think we constantly fight again on the noise issue and wanting to have a good filter, right? So thanks again for sharing that super important information for anyone who wants to do proper PD measurement, right?
Thank you.
All right, welcome back everyone from break. I hope you all had a nice break. Time to stretch your legs, get some coffee, grab a bite. Now we're going to jump into our afternoon session. So I will pass it on over to Mathieu and Mathieu to introduce our next speaker.
All right, thanks everyone for coming back after the break. Hope you have lunch already, have something to eat. Our next speaker is Shanon Lo. She has more than 4 years of experience in high voltage electrical apparatus. She has conducted on-site commissioning testing as well as maintenance testing for the purpose of condition assessment for transmission and distribution utilities. She's also involved with root cause forensic analysis in laboratory for underground cable system, including cable and accessories for various utilities such as Electra, Oakville Hydro, Fortis Alberta, etc. She is currently a member of the IEEE Working Group for investigating and analyzing power cable, joint, and termination failures. Today, she'll be sharing a topic with us that is challenges in testing medium voltage cable in a field environment. Please join us and welcome Shanon to share this topic with us. Shanon, the floor is yours. Please go ahead.
Thank you, Mathieu and Mathieu. Hi, everyone. Kind of nervous doing this virtually. Said that I can't see your face, but thanks for having us today. Sorry, having me today. So I'm gonna see if I can go forward with this slide. Sorry, just trying to do this.
Shanon, you'll just,
Okay.
there you go.
There we go. There we go. Okay, I think we're going that. So I don't know if you have met me before. If you're not, hi everyone. I'm Shanon. I used to be working for Metzco Energy Solution. Now we got acquired by BBA, so I'm working under BBA now. Like Mathieu mentioned, I've been working in this role for more than 4 years by now. So I started my career a little bit more on asset management side of the world. And then slowly moving toward the actual on-site or laboratory testing for different medium voltage class of apparatus. And so recently I started sitting in some of this working group in the 400 series, which we're going to talk about a little bit more in a couple of slides, which is mainly for conducting few diagnostic testings for medium voltage class shielded cable. So which is very interesting for me, and I'm excited to share it about that with you guys. So I'm just gonna go next slide. There we go. So for assets or for cables in general, there are so many time of its life that could be tested for various reasons. Starting from the factory, when it's done productions, typically standards required the manufacturer to do testing as a routine test to make sure that the cables were manufactured properly, that there's nothing wrong with it before it gets shipped out of the factory. So that's we call factory testing. A second phase of where PD or partial discharge testing is going to be done on cables would be in the field environment. Right here, I only highlighted two type of the mainstream, like commissioning testing and maintenance testing. For some of the more important or critical assets, I know there are users out there that would do and one more layer in front of the commissioning testing, which is the acceptance testing for the cable itself, just to make sure that there's nothing wrong during the shipment, that the cable is in good conditions before it get installed in where it should be. And then once everything's in place, it's all installed, terminations, usually with the terminations, installs, or if there's any splice, then it goes to the commissioning testing. As is what it is, it's just mainly doing the testing on the brand new cable or brand new installation. Um, you know, a couple of you may already know a lot of issue when it comes to installation is workmanship issue. Although we would like to have our worker for work very well, but once in a while there's a mistake here and there, and lots of user would like to get that um, assurance that there's nothing wrong with the installation before they start energizing it. So that's where PD comes in handy when it comes to detecting some of the installation error or workmanship error when it's brand new installations. And then another time that when a cable is in service, some more users starting to do maintenance testing for on-age equipment, where we say this is a condition assessment because we with the constraint of labor and lead times and money wise, it's always a good idea to start looking into prioritizing which cable segment to get replaced first, which goes after, and so on. So we see more and more requests on doing partial discharge as a part of the condition assessment. Again, it's what we have seen so far is the cable these days are made very well, and a lot of the installation were done back in the 90s or 80s or maybe early 2000. That wasn't that many people doing commission testing back then. So if there, like I said earlier, if there's a little bit of installation error and all that, that's start growing into, down the road 20 years, 30 years now. And actually those location accessories, we're talking about splices, we're talking about terminations or elbows, they're usually the one that gets failed first rather than the cable itself. So when it comes to replacement strategy, it's easier or cheaper in a sense that to replace this accessory rather than the entire cable itself. So this is where partial discharge come in handy when it's helping the user to, you know, be wise on spending money for replacements or any asset management strategy. And last but not least, that once the cable is done its serving, some people may choose to send it to a laboratory for a more thorough testing. That could be all kinds of electrical testing, plus waferings and microscope analysis and all that. And then typically, not typically, but a partial discharge could also be done at this stage as well on this not used cable in the field. So next one. So unfortunately, or is it fortunately, that field is never really well-controlled environment. For example, for cable in the factory, like I said earlier, there's a requirement to have the cable to be, let's say, not having any partial discharge level more than 5 picocoulomb. So imagine your threshold is already 5 picocoulomb, so your background noise in the lab or factory shouldn't be more than that. Otherwise, you're not able to see if it's around 5 picocoulomb. But when we go to the field, that's no longer the case. It would be nice to have that 5 picocoulomb, less than 5 picocoulomb environment in terms of background noise, but I want to say it's never really the case anymore, because there's so many things that's going on in the site. And in the next couple slides, I'm going to go through what are some differences between the lab or factory versus the field, because it makes a difference as to how useful or how do you use that information from PD to get what you want to understand. Like I mentioned earlier at the beginning, there's this IEEE standard 400 series that's helped That's a guide for users to understand what are some of the practice for doing diagnostic testing on shielded power cables. There's this particular one, REEE 400.3. We just got a new version end of last year, early this year on partial discharge. Yeah, it's very important to know that field is definitely not the same as factory slash lab or any well-controlled indoor environment. In the field, it's subject to a lot of noises. I have been into situation where that there's something like a motor or generator that's running around it. You don't know what kind of like if you're in a residential area, what kind of like loading that's going on. Is there any other electronic noise that's in the system? So it's really hard to control what's there. At the same time, cable may be connected with accessory with lower ratings, and is it even putting the same test voltage? Does it even make sense for the entire cable system where your cable is rating for one thing, but your accessory is rated for another thing? Is it a fair ground to compare with? So in the new version of that 400.3, now there's a number there that kind of start focusing on the inception and extinction voltage versus the actual absolute magnitude that we would have been doing in a factory environment like the 5 picocoulomb that I was talking about earlier. And most of the time that when we do cable testing on site for partial discharge or under any other purposes, most of the time, I wouldn't say except for, I want to say mainly for maintenance or condition assessment, we don't do the voltage, test voltage more than the rated cables, because definitely that's not like doing the testing is not to fail the cable, but it's, for maintenance purposes, more just to know what's the current condition of the cable right now. So sometimes for me, it's kind of hard to get that message out that its feel is definitely different from a well-controlled environment. So it's not fair to put the same criteria for lab testing versus a factory testing, or actually, and a field testing. Sorry, I keep saying lab. So like I said, what kind of field environment are we talking about? Even in the field, there are so many field. And when I say field, mainly I want to say it's not well-controlled environment. Most people would think, okay, it's gonna be outdoor, but it could be indoor at some time. So I pose a couple examples here that I usually go to, like for example, outdoor substations, where it could be everything is energized around you except the cable. Same as indoor substations, a lot of these industrial owners, they will have their own little substation, their own little switch gear to distribute down to 600 volt. So these substation, they're usually in the switch gear, and these cables are connected switch gear either to another switch gear or to the transformer itself. And depending on the situation, for example, the testing that that was in this picture in particular, actually the rest of the switchgear were live at the moment that we were testing. And last but not least, there's always this outdoor residential's cable testing that we do for condition assessment as well. So you see the field environment could change one to the other a lot. And there are various factors that plays a really important role when it comes to PD testing on site, especially. First of all, it's the weather condition. Sometimes it's snowy. Look at the picture that I have on here. This is a project that we did a couple of years ago. You see this little nice snowman in the back. So the weather could change anytime during the day. And it's kind of important to know what's going on. Snow, it's kind of obvious, but when it's like just couple drops of rain, sometimes you can't see it. But when we do our testing or measurement, it kind of shows up on the PRPD. Like, you know, you start seeing some random stuff here. People like, there wasn't there just 2 seconds ago, and why is this happening? And because with our PPE on, like I have my PPE that's long sleeve and I have my hard hat on. Sometimes it's hard to know it's raining if it's just a couple drops. So it's important that you know that it's happening. I usually start looking at the ground and I know that's raining. And then wind, surprisingly, it's another factor for, at least for me, for our testing, because we usually have like one fine test lead connecting one device to another device. So if that, because that lead's kind of light, so when it's windy, it starts shaking a lot, like moving a lot. So then that shit can kind of create a little bit partial discharge as well, and it's mess up our readings, and the PRPD just got crazy and all that. So, you know, that weather definitely plays a roadblock for us. And the same time, the site condition, I wish I can pick it, but it's not. There's many factors or situation where it's kind of difficult for us. For example, in this case, I have some nice cute dogs and cute cats. That was one of the sites that I went to last year. It's a nice rural area, and all these families, they had their dogs and cats, but they were never on leash or you know, cabinet in house. So, you know, with our coupling caps and all the equipment that's out there, you know, they play, you know, you have to be like controlling them not to get any closer to the equipment. And sometimes we're on a slope, so for the capacitor, it's kind of like hard to set it up nicely so that it's not tipping over. And for some of the construction side, like I said, like sometimes we do commissioning testing, and then sometimes they call us in the halfway through the construction. Hey, we get this cable done. Can we get the testing going now? And as you can imagine, some of this side, they're very congested, very, you know, there's definitely some housekeeping required on this side. And what's challenging is we have difficulty finding enough like clearance from nearby metallic object. Like sometimes they're like, oh, like we have this many things around it. Like let's set you up right here because that's the only space that you can have. And you know, it's always hard to isolate that from the environment where there's like some, let's say there's some guardrail, there's like scaffold, that's like they're all metallic, and you know, once you raise the voltage up high enough, they start showing on your measurements as well. And noisy environment, like it's always a number one enemy. Physically noisy, it's happened in construction sites some of the time when there's like not directly right next to you, but could be like somewhere like 10 meters from you. But if you have like a, you know, something going on there, you know, first of all, most of you may think, oh, it's not really related. But for us, it's always like the first sign to see if there's anything start arcing. You know, it's easier to tell. Like, you know, I don't have to look at it. I can hear it. If that arcing, it's arcing. And sometimes it could be just, another thing is like the clearance issue. If there's something floating around it, you can hear it too. It's corona discharge, right? So it's pretty easy to capture it when it's much quiet environment. But when it's like noisy, you have all kinds of parties that's going on the site, that's almost not possible for that to happen. And another important noisy is electrically noisy, right? Because it definitely affects what kind of measurements that you're getting. Like I said, I've been to a situation where I'm like literally set up right next to a generator, the rotor. They're creating a lot of like interference to your measurements. Like I've changed it like so many different bandwidth, like my measurement frequency, like it changes so many different spots. Like there's one spot that's nice, but you have like so many spots that's not, you know, when it comes to like this, like the IEC 6270 that everyone referred to, is no longer really too useful at that moment because nothing worked at that point. And same as similarly, other than that electromagnetic field that's around us, your input power or your power source is another factor as well. That it could be noisy as far as like it has a bunch of electronic noise, like the diagram that I'm showing on above on the top, and then import like your power source. Sometimes we do rental, sometimes we have our own equipment, sometimes you get shipped, it get bombarded here and there, and sometimes it's hard to differentiate whether that partial discharge is actually generated from your cable that's you're testing, or is it actually from the power source that you're using, because it means totally different things, right? So these are some of the things that you really have to consider when you do the assessment on site. Down. So other constraint, there's safety, of course, like other than the electrocution for exposed, coupling capacitor or your filter or even your power source. Especially when it's come to online PD where we use HFCT where you could connect it to a neutral or concentric neutral or cable shift. You're getting proximity to very close to a live equipment that definitely is another higher risk than as well as offline. That's a risk of safety already. Field environment. Another thing that's really difficult is time constraint. A lot of time it depends on the setup of the system. It could be we're doing the condition assessment as an outage. So, a lot of user definitely would like to shorten the outage time as much as possible. And as well as like the time that we can actually do things. So it's not just the testing time, but it's also this like setup time and, returning everything together time, right? So that all adds up together. And that keeps the pressure as to like how measurements, how long the measurement should be taken, how much voltage, how much granular can that testing could go. One more thing is the visibility to another end of the cable. If you do like an end-to-end cables, like if it's short cables, yeah, sure, you can see what's going on. But combined with the time constraint, there isn't really much time to travel back and forth and see what's going on. Like with the nice localization, yeah, sure, you can say, okay, it's from the other end of the cable. But is it really a problematic issue that's we are finding, or it's just some other stuff that we could have fixed easily? For example, if I have my cable that's in the residential area, what we usually do, we park like cables in one of these stand of bushings. So let's say if someone didn't know it well enough and they put it in like two ends bushings and one side's open. Now you're gonna start seeing a lot of discharge, right? Showing at the far end. But if you don't know that situation, okay, it's actually not your cable, it's just like someone didn't close it well enough so that there's no PD issue from it, that it's gonna mess up your understanding of like what actually happening. Again, another one, it's sometimes there's a software glitch. It just my laptop doesn't really work well. Sometimes not responding as fast as it should be. So, doing a little check of your system is always a good idea, doing testing, like on-site testing, because you just never know. And last but not least, there's also equipment damage during shipping. Sometimes I have to go to this very far places, and I trust my courier to have it shipped nicely. Sometimes not. So I definitely recommend carry on with you if possible. But when flying with all this equipment in your suitcase or in your carry-on, you get questioned a lot. So I try to minimize that too, but sometimes it's just not possible. And so, with all this constraint on site, with all this uncontrollable factors on site, the number one question or the analysis at the end, what we're trying to answer is the PD really from the cable? Is it really? So some of the thinking that could have been done on site to help you kind of isolate and make that conclusion, I can list it here. what's actually going on around the cable that we cannot see. This is kind of similar to what, it's similar to the situation more like the generator case that I was saying. Like, we're seeing something, we get coupled by something, or, the clearance that I was talking, is it coupled by there? Or is it the bushing? Is it something that I cannot see right at where I'm sat at? And it could be something that it's not totally related to the cable itself. And second question, is there anything that's around my side was not done properly? This is more mainly mainly for the clearance issue that I was talking about. Or sometimes I do something very stupid, like I connect the feed connection to the PD connections and vice versa. And I was like, why is my system not working? Just because this is something so stupid, like I just didn't connect it properly. So sometimes it's something that you have to look at as well. Is my test setup clean? This is related to the power source problem that I was talking about earlier. And not even just that, but in my test setup, I do quite a few tests, like a homemade test lead to connect to the end cable at the end of the day. So is everything up to the point of that test subject, is it free of PD? If not, how is that going to affect my result? Like, how does that affect my reading at the end of the day? And measurement frequency, is it sufficient? Sometimes you may want to do a wide band, sometimes you want to do a narrow band. That's always depends on your preference and situation as well. And as well as, is the system sensitive enough to pick up the PD? Again, the level of background noise is always never controllable. There are times that I have like very low level of PD. There are times that I have high level of PD, and it's kind of important to make sure that it's actually capturing something, right? So one thing that I do on sites, like I just create something, just like create something that's peaking in the air, and just like kind of purposely do a corona discharge in air, and just apply some voltage, and it shows up on your screen pretty quick, and that's how you know that your system is responding if there's actually something going on the cable itself. And another thing to consider is, like, is there a multiple source of PD? Can we localize it? Can we differentiate it? And so on and so on. And another, other functions like 3-FRAC or 3-PAR, are they useful when it comes to finding where or what the problem is? That's the end of my presentations. I hope I didn't talk too fast. And yay.
All right. Thank you very much, Shannon, for your presentation. I think it really nicely described, I think, especially some of our customers is also service provider. It really nicely described what could be the challenges that they are facing, they could be facing if they wanted to ever, start a business, side business doing PD testing on cable as well. So I think that's certainly a nice summary of that. So let's use the time to address some of the questions on the floor. Just give me 1 second. I am scrolling that. So the first question, certainly like that question. Cable being purely polymeric organic insulation system, how is it they can survive with PD? I would expect the PD to eat through the insulation quickly. Is the PD in the cable insulation or at connection? I.e., should we not have PD in cable insulation at all? I think it's a great question. And Shannon, that'll be to you.
Sorry, you got one, like the second sentence. Well, sorry, can you repeat that second sentence again?
Yeah, no worries, no worries. You can actually read that on the Q&A part as well, but let me read that slowly also. So cable being a purely polymeric organic insulation system, how is it that they can survive with PD? I would expect the PD to eat through the insulation quickly. Is the PD in the cable insulation or would it be at the connection? So basically, should we not have PD in cable insulation at all? That's more or less the question.
Okay. So I guess that's like kind of related to at the factory states, or I hope I understand the question correctly, right?
Yeah, I think in
Ideally,
general,
yeah, definitely yeah, if it's as I heard Kirchenmayer like solid installations, right? So that's that's the key word that I'm
So,
getting here.
no,
so
worries,
I think the question is mainly focused once you have PD in a cable in an operation that's energized, um, how long will it survive? And if it will fail, how long do we have until failure of that specific cable if it has sustained PD activity?
Okay. Now I understand the question now. Thank you. So having PD in the cable definitely not a good thing. Like that's no one want to have it. But it's why when we do on site, we start looking into inception and extinct voltage. Like I mentioned earlier, it's it's important to know where or when it comes in, because if you, let's say it, and it kind of tells you what kind of problem it is too. Like, if you have an inception voltage of like at your phase to ground voltage, meaning that the whole during your entire like operation, this partial discharge issue is there. First of all, definitely it's not good because it's always there. And then eventually, yes, it would eat through your insulation and you're gonna have a failure. But what we know for sure that this is not generated from electrical tree right away, because you know basically you see it at that moment, everything failed at that point. But what's also important is extinction voltage. Like, for example, if you have an inception of 1.3 U naught, but your extinction voltage is your, let's say, 0.8 U naught, meaning that if there's an incident that somehow your system's going on and there's an over voltage, that it happens all the time, right? And it won't go away on its own. It's always there, you know. Then it's become a more problematic problem because you never know when this oversurge is going to happen, and when it's never go away, it eats through your installation way faster than the other ones. So when you ask the question, say how long can you use it for, it always depends on your inception and your extinction voltage to kind of get that conclusion. It's like how long it can be there for. But does that answer your questions? I hope
yeah,
so.
certainly, Shen. I think we can also add some of the comment because we also see the question there. Mathieu, maybe quickly.
No, I think Shannon did a good job at answering that. Maybe yeah, I mean, yeah, for sure for polymeric cable, in operation you shouldn't have PD activity. That's really what we want. That's why PD in the factory is tested at such a high voltage above the operating voltage. There's a small distinction that we can make between XLP and EPR cables. There are two types of cable that are considered polymeric, but the EPR are gonna have some sort of what I can call inorganic material that makes it a bit more resistant to electrical trimming. But still, in operation, you shouldn't have PD in those cables. I think that's the bottom line here.
Mm-hmm. Yeah. All right. Next question, Shannon. So one of the audience mentioned that they have heard about fiber optic acoustic PD sensor being used to monitor cable joint or termination. Is this something you have seen or have thought on?
I guess I've heard about it, like permanent like PD sensor around the joints, splices, depending on which one you call it. It's I've heard like so many cases in more like transmission line, because like they're more critical assets. Um, Definitely that's helped you with localization, and it's always nice to connect it to your either your control room or a SCADA, because it's kind of like there are people out there that would do like a alarm, like a threshold, like once you see the trending going up really fast, or you see a spike in the level of partial discharge, that's when you have to start looking at it more closely. I definitely have heard about it and definitely love the idea of it. It just always comes to the investment, to at which point it's a good idea to install those one at the joint boss. or manhole sometime.
Sure.
So
Yeah.
thank you, Shannon. One more question. I think we have time for another one.
Okay.
Can you or have you seen PD in 5 kV rated cables? So not focusing on what we could say usually medium voltage or even higher at 5 kV cable. And I can even add to that question. Can you make a distinction between shielded and unshielded 5 kV cables?
Okay, then let's go with shoot it and shoot it first, right? So unshoot it's. I hope I don't have a picture of the cable. I was just explaining to someone else yesterday. So, you know, you have your conductor, you have your insulation, right? And most of the time you have shoot a cable with another layer of metallic shield around it. You know, it could be a piece of wire like concentric neutral, like you have a bunch of wire that goes around it, that's concentric neutral, or it could be tape, which means you have a copper tape that goes around it, and so that's your shield. So when you have that combinations on your cable construction, that's shielded. When you don't have that outer layer, then it's unshielded. I hope that makes sense. It's easier with an example, like the actual sample. But when it comes to, I think the first question was about like partial discharge for 5 kV cable, if I got that one correctly.
Yeah, this is correct.
Yeah.
So have you seen any PD in 5 kV rated cables?
That definitely have seen them, right? Like it's I also almost want to say it's not really, when I say medium voltage, like it kind of like range between 5 kV to 44 kV, or even I think that's a new definition now, or someone put it even higher. But my understanding of like medium voltage always around that level, or even I think the newer standard they try to put it in 2.5 kV to 44 kV as well. So that 5 kV definitely sit in there, and definitely it PD will happen for sure. And it had happened as well. So does that answer the question?
Yeah, I think so. Yeah.
Maybe one last question before we go. Is there any way to determine or assess how much electrical background noise will be presented for a given environment? So how I interpret this question is basically maybe Shannon sharing a little bit of experience in assessing the background noise in an environment, you know, whether it's a field or laboratory environment. How would you do in assessing the background noise level?
So like, I mean, I was trying to understand the question. Like, how do you determine a background noise is a background noise? I guess that's the question. I don't think. So there are a couple background noise that I do consider. First of all, it's before everything is energized. Of course, like that's the presumption that hopefully there's some calibration could be done. I have been to a situation where calibration is not even possible. You know, and at that point you can only see nothing. A trick to do it is maybe shift your measurement band to somewhere else that is a bit more quiet, we call. But you know, before you get energization, you have a floor. You're on your PRPD, you have a floor. I use the PRPD more often. In this case, you have a floor. And then once you energize it, one trick that I do is I'm usually apply, let's say, maybe like half a U-naught or 0.3 of a U-naught to the cable system, hoping that hopefully, because it's still used at the moment for condition assessment, so usually there's no PD inception at that level. And so once that get energized, like say 0.3 U-naught, and that background level, that noise floor that I'm seeing on my screen, that would be my final background level that I'm considering. So then this is how I determine, okay, this is my sensitivity as far as the PD magnitude. Does that answer the questions?
Yeah, I think so. Thank you for that, Shannon. I think we'll address actually, so when I say one last, actually there's another question, but I think that's more towards us, which is which is the question regarding more on the equipment side. So after changing the PD center frequency, well, actually PD software. So after changing the center frequency, bandwidth, any aspect regarding frequency, must we always perform a new charge calibration for OMICRON PD equipment? I would say it applies for any other PD equipment in general. So quickly, maybe Mathieu to answer that.
Can you repeat the question?
No worries. So it's just after changing the PD software center frequency bandwidth. So any aspect regarding frequency, must we always perform a new charge calibration? So I think that
it's tough. I mean, charge calibration usually, if you really want to follow its definition, you need to be in the IEC 6270 range, and not even in the range. You need to be compliant with the standard. Outside of that range, we call it more either a normalization process or sensitivity check. If we consider this question in the topic of cables, what we will do, we will still perform a sensitivity check at different frequencies if you will change the frequencies, just to make sure that you can still see far away in the cable. That's usually what we will do. So, but it's important to make a distinction between the calibration and what we can call a sensitivity check, actually. Yeah.
Mm-hmm. All right. With that, let's move on. Thank you very much again for joining us and sharing the topic, Shanon. Thanks a lot. We'll see you again pretty soon. Mm-hmm. So let's move on with the our next speaker.
Thank you, Shanon.
Mathieu, I think you're muted.
Whoopsie.
There we go.
Don't know why.
All right.
Sorry about that. Coming back to our next speaker, we have John Carlos joining us. So John Carlos Hernandez-Mejia. Also JC. That's what we've been using for in our discussion. So JC has been with Georgia Institute of Technology, particularly with NEETRAC. NEETRAC being the National Electric Energy Testing Research and Application Center. It's part of Georgia Tech. I'm sure JC can share some details with us on that also. So JC originally from Venezuela, attended the University of the Andes in there, and received his Bachelor of Science in Electric Power Engineering in July 2000. He received his Master of Science in Electrical and Computer Engineering from the Georgia Institute of Technology in Atlanta, Georgia, around 2005, and his PhD also in December 2008. From 2008 to 2017, he was a professor at the University of the Andes in Venezuela. In 2018, he joined NEETRAC as a full-time researcher, and now as a senior research engineering lead with the data analytics and diagnostics laboratory. So JC and I and us actually met in the IEEE standard group as well. So also as an active member in both the IEEE PES group, constant also a member with the ICC as well. So thanks again for joining us today, JC. Today he'll be sharing topic with the also with the cable to us. So his topic will be diagnostics integration for commissioning of critical power cable systems. So thanks a lot, JC. The floor is yours. Please go ahead and we'll share that presentation.
Thank you, Matthew. I just want to make sure that my audio is coming through properly. Can you hear me?
Yeah, yes, all good. Thanks a lot.
Okay, excellent. And then let's make sure I have the presentation for Rochelle. Yep.
So you will just click on the slide and use a page up, page down button.
Oh, okay, excellent. Thank you so much.
There you go.
Rochelle,
You're
for
welcome.
reminding me that. Okay, before we go to the technical part of this, thank you so much to Mathieu for the invitation and the opportunity to present in this industry forum. So the presentation today is related to how you can integrate different diagnostic technologies to basically maximize reliability, and specifically in this case will be maximizing reliability for a new power cable system. But before we go, in detail through the presentation, so a little bit, more about me. So I'm pretty active in IEEE, PES, ICC. So that's the Insulator Conductor Committee in the 400 series. So that's basically sub F, the subcommittee F, which is the one related, to with diagnostics. So right now I'm serving as the vice chair for the update of IEEE 400.4, which is, diagnostics using damp AC voltages. And I'm also was part of the working group of the recent standard IEEE, the update for the recent standard IEEE 400.3 that Shanon just mentioned. So related to, what NEETRAC is, so we are a research lab, part of the Georgia Institute of Technology. We have 28 years of experience, doing cable diagnostics and then other activities related to, in general, distribution and transmission systems. It's a pleasure for me again today to be here and present to you this material. Okay, so because we are a state institution, so basically I'm forced to do this for this type of presentation to give you this notice. So going quickly through this, let me see if I can get my pointer here. Okay, let's see. Okay, I'm not able to find it. So let's go with that. Okay, so the information that we're going to be presented is our best knowledge that the information is accurate. We are not responsible if you use this information and to do something and you get hurt. We disclaim any warranties. This presentation is not endorsing any product or procedure provider, and then the copyright remains with the Georgia Institute of Technology. Okay, so this is how the presentation is going to be structured. So we're going to review some background about, what commissioning is, and then how diagnostic technologies are important in that case. Then we're going to define what a critical power cable system is. What are the parameters to define them, and why, in general, you want to maximize reliability for that specific type of circuit. Then we're going to go, to review our view on how you can maximize reliability by doing the integration of different diagnostic technologies. And we're going to be focusing, because we're talking about commissioning, so it's a new power cable system. So we're going to go all the way from the design to the factory testing, to the site acceptance testing, to the installation testing, and then maintenance. And towards the end of the presentation, we're going to review other important steps that we have to take into account if we want, to have a new a power cable system, maximize its reliability. And then at the end, we're going to do review some summary conclusions. So the background. Utilities and in general, the users of power cable systems, they do recognize the value of commissioning testing. So basically, commissioning testing is there to basically make sure that all the way from the beginning, you have some level of quality in the construction of the power cable system, right? And we're gonna review that with the pipe plots. But in addition to that, there is also value in doing maintenance testing. And in addition to that, right now, today, we have a variety of technologies and criteria that can be used to do the condition assessment of power cable systems. And why this is important? Because if you see there, the pie plots, the one that we have in the lower left corner, so that's recent data on a medium voltage power cable. You can see the reference there on where the failures are typically happening for power cable systems. And as you can see there, the majority of the failures are in the joints and in the termination, so in the accessories. And if you see the reasons, which that information is in the pie plot next to that one, almost half of this is related to poor workmanship or workmanship errors, so installation errors when we are, constructing, installing the cable system, or we're repairing the cable system if it's a cable system that is already deployed in the field. So it's important, again, to have diagnostic technologies to be able to capture those cases in which, we have workmanship errors or, some issues related to the accessories, etc. So you can see there the second, the most important one will be manufacturing with 15%, and then the electric breakdown, which is related to the system not able to withstand voltage. Okay. So now let's go and define what is a critical circuit. So a critical circuit, the definition of a critical circuit may change from utility to utility or from cable user to cable user. And therefore, specific cases to define a critical circuit may have different parameters for definition. But in any case, regardless of utility or the parameters, a critical cable system can be defined as a system that if you have a failure in that particular cable system, then the consequences are considerable. And those consequences can be related to many aspects. For instance, for example, the critical circuit is feeding some critical infrastructure like a government or a military base, etc. Or like the water supply for a city. Or it can be also related to safety, or it can be also related to access to the circuit. Meaning it's really critical. It's really hard to install the circuit. So if we have a failure in the future, then it's going to be really, really hard to do a repair. So that may be a different criteria to define a power cable system as a critical circuit. And you see that right there. So another one, that I forgot to mention is impact to the reliability and then impact to the customer. And I'm going to be presenting here a case study in which the criticality is actually defined by several factors, but mainly the impact to the customer. So economic loss specifically. So again, this can change from utilities to utilities. The parameter can change to define a critical cable, power cable system from different users. But at the end, what we are trying to avoid all the way from the beginning is having a failure in that cable system after the cable system has been commissioned. And that's the main goal, or what we're discussing today. What can we do to be able to maximize that reliability for that cable system? So this is our view on how you may be able to accomplish this. So basically the answer is you have to be involved all the way from the beginning to the end, and then to the operation of the cable, of the power cable system. So the end will be the operating life of the system. So as you can see there in that kind of process that we're trying to articulate graphically here. So we're going to start with A, which is you have a need. And in this case, we're defining this as an utility need. So you have a need for a particular power cable system that is critical. So for that utility, that power cable system is critical. So the first thing that the utility have to do is think about it, which is the purple kind of arrow there, and you have to think about what is the system design that you're going to have. It's going to be what traditionally you are using in the utility, so like the same insulation type, or you have to consider, a different type of insulation type because, this is critical. For instance, maybe, go from XLPE to EPR because you need more flexibility, or you're concerned about, maybe electrical trees, and maybe you think EPR is more, PD resistant. Yet again, you have to think about your design, and that's including the cable, which we always think about it, and also the accessories, which we typically forget about it when we are talking about a cable system. Cable system is cable plus accessories, always. And both of them are important, because if you have a failure in one, in the cable, then you have a failure. And if you have a failure in the accessories, then you have a failure. So the cable system is not able to operate. So once that, design is kind of, ready, then you have to be thinking about from where I'm going to be getting my materials to build this, critical circuit. And you can go, several ways. So you can do a bid for someone to basically install and build the system for you. Maybe you can do it yourself, or maybe you can do that with your own contractors. The point is, regardless of what you're doing, you want to maximize reliability, and whatever you do, you have to take a closer look on the manufacturing, and then the accessory selection, and then how you're taking all these things to the site. Again, making sure that there is no damage to the cable, and then that the accessories are the highest quality possible, etc. So once we go through the manufacturing process, before the cable and accessories are actually shipped to the site, then you have to do factory acceptance testing. And we're going to go through that a little bit. Then you do the handling, you get your materials to your site, and then you do site acceptance testing, that's SAT, here in the graph. So you do the installation, and then during the installation, you're going to be doing installation acceptance test. So that's going to be IAT. And then if everything goes okay, it passes all the testing, then the system will go and enter the operational life. So that's basically what is represented here by the green cloud. And of course, because this is a critical system, even though it's new, at some point in the future, you will have to do another instances for cable testing and assessment in the future, making sure again that you have the maximum, the highest reliability possible for your system. Okay, so we're gonna walk through this using a case study that we actually did here in the lab. And it's basically a bay crossing somewhere in the US in which you have a near end and a far end. So the circuit that we're going to be talking about is more or less, you can say, 2 miles long, 12,000 foot, 12,000 feet. And then because of the cable we selected, limitations in the reels and all of that, the utility decided in this particular case to have a joint in the middle. So having you need a cable of 2 miles in this particular case wasn't really feasible for the utility. Okay, so this cable system is feeder type, is 3-phase, it's a bay crossing, and the design we had in this case included one spare. Just in case you have, a failure in one of the phases, then you have one spare already installed to transfer, the phase that failed to that spare, and then again having some kind of redundancy in this particular case. And then one important factor here for this case study we're going to be reviewing is that 2 cables are installed at a time because of barge limitations and material limitations. So only, let's say, phase 1, phase A, phase B are installed. Then we have to basically go back again, gather materials to install phase C and the spare. So that's what it means that 2 phases are installed at one time. By the way, this is a medium voltage feeder type. Okay, so let's see what happened. What happened with the factory acceptance testing. So If you're doing this, you need to do more than what you typically do for factory acceptance testing. You have to request it to the manufacturer. You have to do a little bit more. So for instance, you can consider that you can witness, send someone to witness the factory acceptance test in the factory. And you can also request, okay, because this is a critical system, I want you to do the testing more regularly for the cable. And of course, maybe considering augmenting, again, the testing, and then, having more stringent requirements for that case. And then you can see here in that pie plot that from all the material that they manufactured for this particular case study, only 2/3, more or less, of the material actually was in good condition. Some of the material failed the PD testing, another material failed the withstand testing in the factory, and some other material that was originally okay got damaged in the factory because, maybe a forklift, ran through, it crashed with a reel, etc. The point is, you have to do this because not 100% of your material is going to be okay, even at the factory level. So again, the materials get manufactured, they get shipped and handled to the site, and then specifically in this case, we do this for the cables. Just making sure that the cable reels didn't suffer any damage during transportation and handling. And these are the tests that we deployed in this particular case. So visual inspection, just to see if you see any damage to the cables. Then you do TDR, that's time domain reflectometry. For those of you who are not familiar, it's basically a radar test. You send a fast transient pulse through the cable, and then you see reflections. And that's giving you information about the cable structure, cable system structure. And for instance, if there is a damage in the cable that is causing a change in characteristic impedance, you may be able to see that in the TDR. And then we do VL left and delta, just to have again a reference for the cables, and then a PD at the end, just to see if there is any partial discharge activity in the cables after they were again manufactured and then handled and shipped to the site. And in this case, I mean, all the material, cable was okay, and then everything passed the site acceptance test. Now, this is going to be the fun one here, which is basically the installation in this case. So in order to have this a little bit clear, so let's define 3 stages for installation in this particular case. So remember that we're having to cross about 2 miles, and then we're going to have a joint in the middle, right? And only 2 cables are installed at the time. That's why here in the barge, this is a representation. You see those figures. It's a representation of the crossing and then the barge, and then the joint is actually represented here by the green ellipse. So stage 1, we call that joint acceptance. So basically, you install half of the cable. You're in the barge. You build the joint, and before the joint gets submerged to the seabed, you test the joint just to make sure that it was properly installed. Then after that, then you go through the process and then get the joint in the seabed, and then because you may have some tension there, and it has to go through the trencher, the joint have to go through the trencher, etc. You do another test after the joint is in the seabed, again, to make sure that the joint going from the barge to the seabed didn't suffer any damage. And if that's okay, then you keep installing, you continue to install the cable, go to the far end, and then you do a final typical conventional commissioning testing, just to make sure again that second half of the cable was installed properly. So that's the phases. And here, we're just gonna review the tests that we did, and then we're gonna review the results. So, and this is the integration part. So PD grade is gonna give us location of any potential defect if we're able to detect it. But if you're integrating this with another technologies like TDR or tan delta or even PD at different voltages, different voltage sources, then you're maximizing again the reliability, and you're maximizing the probability you're going to be able to see something if something is not really right in your cable system. And that's why, you know, integration of diagnostic technologies in the proper way helps you a lot. And of course, these tests that you see here were deployed in sequence, and you can see there the references, standards, and guides. Okay, and basically everything was based on IEEE 400 series. So before stage 1, stage 2, where, you know, again, after the joinings in the seabed, we repeat the TDR, then we do a PD using the AC in this particular case, and then we verify that PD reading by doing PD using VLF. And actually, this is a monitor withstand test using a partial PD at VLF frequency. And the final commissioning testing, so this is where we deploy pretty much everything. So again, TDR, then PD, then VLF tan delta, and in this case, we do VLF tan delta to have that value as a reference for the future. If you want to, you know, redo in the future some tan delta measurements and maybe see if you are having, you know, some insulation, uniform degradation, if you have water ingress, etc. But it's important you do this at the beginning so you have a reference to use as a basis for the future. And then again, PD, monitor withstand test with PD, and then verification of that using the PD at the end, using, in this particular case, damp AC voltages. Okay, so let's see the interesting results we got in this case study. So this is the first cable that was installed. So in stage 1, again, the joint in the barge, it tested all good. Now, the joint, while the joint was going from the barge to the seabed, it suffered some mechanical damage because the payoff of the reel and the barge speed were not really matching properly. So basically, you have a high tension in the joint that basically damaged the joint, and the cable system has to be abandoned. And you're going to see later how we detected that, actually. And this is the way we detected. So here you can see the TDR traces before and after, meaning stage 1 and stage 2. And you can see here the red when the joint was on the barge, that you have a typical TDR trace that has a joint in the middle, and you can see the joint trace, etc. But compare that to what we saw after the joint was actually installed in the put in the seabed. So you see that huge negative reflection in the middle. So that wasn't really good because basically the joint got pulled off, you have water coming in, it's actually salty water. And then we are seeing from the TDR that you had a kind of a short, at the joint location. It was verified, and basically that's, we verify that, the joint got damaged. So you can only imagine, like for this critical circuit, if you don't deploy any type of diagnostic technology, you have this situation, you keep the installation, and then when you are energizing the cable for the first time, then you're going to have a huge failure. So that's why, doing diagnostic testing is important in this context. Not only that, this is the other cases when they were installing the cable 2 and cable 3. Remember, we installed 2 cables at the time, so cable 1 and cable 2 were initially installed at the first go, but because cable 1 was at tandem because of the joint damage, they have to basically stop the operation and then cancel the installation of cable 2 and then come back later and reinstall cable 2. Now, for the reinstallation of cable 2, they had to rejoin cable 2. And then in that particular case, we detected PD when the joint was in the barge, meaning stage 1. You're going to see the results. So we detected the PD. We make sure that the PD was coming from the joint by having sensors deployed in the barge and then analyzing, similar to what Shanon said earlier, verifying the pattern, the sensitivity, etc. So we concluded the joint had an issue. We cut the joint, took the joint to the lab, and we did some dissections. And I'm going to show you what we found in the joint when we took a look to the joint in the lab. Eventually, they put another joint. It tested okay, and then we move on to cable 3. In cable 3, we saw exactly the same. In stage 1, we detected PD at the joint, cut the joint, send it to the lab, rejoin, tested okay, and then it tested okay after that for stages 2 and 3. And then the other 2 cables that were tested, they tested okay, but before doing that, these are the results for the PD for one of the cases when we saw PD at stage 1, and you can clearly see there that in the PD results, we're having the PD activity coming from basically, in this case, the joint location. And this is an idea, so you have an idea of the kind of PD pattern that we saw in that particular case. And we verify the PD in this case using 2 sources. So we saw the PD pattern using DAC, and then we verify using the VLA frequencies. Okay, so remember I told you we took the joints to the lab to did some dissections, and look what we found. So basically, they didn't do a proper cutback, insulation shield cutback in the cable, and that's one of the reasons why we were having that PD activity in the joint in stage 1. So basically, this is an indication that having the crew to be aware that they have to do the best job as possible, and then having a supervision maybe when they're doing the installation is really imperative if you're doing critical cable systems. And then cable 4, cable 5, they tested both okay in all stages. So that's that. So what additional steps can you take if you have critical circuits? Again, you have to think about your proper cable design. So for instance, if you're considering the case study I just presented to you here, so the design gotta have for sure some type of water blocking in the conductor, which is typical, but also in the metallic shield. And that's, that's what we mean for this. So you have to think about your cable design, having a cable design that is proper for your application, and then for your criticality. So for that, then take a closer look to the manufacturer. So require qualification reports, how often, what is the quality system they have in the factory. And basically, at the end, you can also do a plan audit that is more than a visit. So we have a formal audit in that case. After the cable is manufactured, you can also do, cable quality assurance, just to make sure that the cable was, from the sampling you do, the cable was properly manufactured, and then avoid issues such as improper. You see, there's the different cases for improper cable construction, maybe having a misapplication of tapes, or maybe some defects in the conductor shield, etc. And then in the pipe plot, you see more or less figures that we see here in the lab, because we do a lot of cable QA for the members here in NEETRAC. And the yellow and the green are basically meeting the standard. So in general terms, you can say 80% of what is coming to us is meeting the standard, and then 20% of that usually coming to us does not meet the standard, which is basically typical following the Pareto, principle of 80-20. Now, taking a look at the accessories, so use accessories that you are familiar with, that your crew knows how to install them, they have experience installing them, and trying to also use the connectors that were used for the joint certification. So again, look at proper accessories for the cable design. And then as a conclusion, summary conclusion here, so we saw a case study of a commissioning test for a sea crossing. You guys saw how we integrated the diagnostic technologies. We discussed why this integration is important. We saw how that was able to detect some issues in the installation and then saving money and then maximizing reliability to the future. And of course, all of these will be reducing cost and impact in the future, again, improving reliability. And of course, the material presented here can be used as a guidance if you have, a different case. By the way, this material has been presented also, if you want to get more details, in the ING Cable conference earlier this year, and also part of this has also been presented to the ICC, the Insulated Conductor Committee. And with that, I'm open to answer any questions that you may have. Thank you for your time.
Thanks a lot, JC. That's a great presentation with the case study as well, and multiple tests that is needed to ensure the cable is working well, right? So thanks again for sharing that. Let's address a couple of questions we have here. You, on one of the slide, I think in the beginning of your presentation, there's a statistics. I think you quoted that from a NEETRAC journal before. The question is whether that statistics include 5 kV rated cables. So the company that this audience has been working with has not experienced a 5 kV rated cable failure in over 50 years of operation. So just wondering whether the statistic apply for lower voltage rating cable, or is it apply for a higher voltage one?
Okay, thank you, Matthew. I will have to go back and look at the reference. I know that this is specifically for medium voltage cable. Now, 5 kV is not really typical for utilities. You typically see 5 kV in nuclear power plants and maybe some industry applications. So I guess it may not be included. So what I would suggest to the person that asked the question is you have the reference there. So take a note and then go and look for the reference and then see if the 5 kV is included or not. However, having 5 kV via medium voltage cable system, and then remember that for the different voltages, the insulation thickness also changes. What I would expect, even for 5 kV only, will be something similar to what is shown here in this plot. I wouldn't be expecting, those proportions to be really too far away from what we see here.
Gotcha. Thank you, JC. But great point. This is actually for a nuclear power plant as well. So great point being made there. So another question is, what damage do you expect from the shipping of the cable, transportation, basically? I assume, so just reading the question here, I presume it is shipped on a spool, covered, and transport in an enclosed truck. Do you have some example of damage, maybe from transportation process, shipping of a cable?
Yes. Mm-hmm. So I can give you, we see many things coming to us, but in this particular case, actually, let me show you, remember this plot here? So there is a proportion there in the top that says factory damage. So those were some reels that were already finished, packed, manufactured, and they were ready to be shipped to the site, and then a forklift ran into them and caused, some damage to the cable. That's one case. In the factory, another case that we have seen here in our lab, you can actually, in some cases, it's not really, frequent, but I have seen cases in which they put the labels, and not in the factory, it's usually in the distribution process, and they put staples through the jacket and then go inside the cable core. But knowing the factory is in the distribution. Because remember, these cables in some cases are not coming directly from the manufacturer to the utility. So they go through a distribution chain. So I've seen those cases, staples, in cables. I've seen cases that you may not be using the best shipping company ever. They don't treat the cable in the proper way. And then you get the cables in the field, and then the cables, they have some mechanical damage, some friction, some, loose ends, stuff of that type of, issues. So those are three examples, and of course, those may be not the only ones. But yet again, the idea here is that you are aware that in the context of criticality, that you have to take a much closer look to this. Again, so you're maximizing the reliability for your critical circuit.
Understood. Thank you for sharing that, JC. I wonder, for the case study you shared, after that has been, commissioned and in service, were there any, maintenance being scheduled there as well? Did they try to find out any maintenance, process to take care of that?
That's a great question. This system has been running now for 3 years. So we suggested them to do an initial tandem measurement 5 years. And so far, what I can report is that the system, as far as I know, it hasn't had any failures. And the idea is for them, to do some inspections from the near end, the far end, but that's basically a switch, a switchboard. And then, from the tan delta, at 5 years, maybe having some indication of the insulation degradation or maybe water ingress, etc. Because remember, in this case study, you're not able to see that cable. That cable is, under 6 feet of sand.
Right.
And probably 30, 40 feet of, water.
Yeah, definitely. Thanks for sharing that, Mathieu.
And thanks, JC, for the good presentation. Yeah, I was just wondering, you mentioned that for step 2, I believe that you were doing a TDR, then you were doing a PD using DAC AC, then VLF, then going back to DAC AC, DAC PD. Could you elaborate a bit more on why you will use both technologies? From your experience, is there something that you will pick from one and not the other?
Yeah, so that's a great question, Matthew. Thank you for that. Yeah, what type of geeks? We try to do this for the members, but also try to throw a little bit of researchy type of things. So when we do this, we're trying to diversify what we do as much as we can, and of course, according to industry standards. And then what we gain from this is, and I'm not reporting that here. For the cases in which we detected PD, we compared the pattern we got from DAC to the pattern that we got from BLF. And then, getting conclusions that are those, similar or are they different? And that's, what we gain by doing that. And also maximizing the probability that if you have something that you're going to be able to see it. Because there is also this issue in industry that, maybe if you do the AC, because it done so quickly, you're not able to see a lot of, PD pulses. So to get that out, okay, so we also did BLF, which basically is exposure for the whole period of time. And then, again, if you don't see anything on using the AC or using BLF, then you have more leverage to conclude that nothing is going on in the system, and that's basically why we consider that in this program in this particular case.
All right. Thank you very much, JC. I think that's about it. If I don't miss any questions here, let me check again.
Yeah, just a comment that may have missed. We don't do this for business purposes, so this is a case-by-case basis, and it's like unique cases that we try to help the members. So we are not really doing this all the time. Just these really special cases that where we actually go and do something.
Okay, thanks a lot,
Yeah.
JC, for presenting. I think super useful content, even for this table, give you an idea on which standard of guide you should look after, if you wanted to conduct such tests. So thanks a lot, a great summary with the case studies as well.
Okay,
With
thank
that,
you.
thanks a lot, JC. With that, we can
Thank
move
you,
on.
guys.
Thank you, JC.
See you around, JC. With that, let's move on to the last slot of the day. So the speaker for the next slot will actually be the person next to me. So my colleague Mathieu Lachance. Mathieu received a Bachelor of Science degree in Electrical Engineering from University of Laval in 2014. After graduating, he worked as test engineer in the field of partial discharges and high voltage. In 2019, he joined OMICRON Electronics Canada Core, where he currently holds the position of Regional Application Specialist of rotating machines and partial discharge for North America. Mathieu is an active member of the IEEE Dielectric and Electrical Installation Society and has published technical paper for IEEE, C-grade, and other industry journals. His current focus is on partial discharge testing and electrical installation system, as well as rotating machines. Today, his topic that he wanted to share with all the attendees is the practical aspect for PD measurement on stator coils and bars. So with that, the floor is yours. Mathieu, please feel free to, I think you need to share the presentation first.
Yeah, thank you, Matthew. I think my presentation should be there, is it?
Yeah, your presentation should be in
Perfect.
the PowerPoint. So you can just press and use page up, page down.
There we go. So our marketing team asked me to switch spot with you.
All right,
So let's do that
do
very
that
quickly.
All right.
Good.
I can adjust this as well.
All right, so yeah, good afternoon, everybody. I think you've heard me talk a lot during the last 2 days, so that's, I promise, this is the last presentation for the symposium. Today we'll talk about practical aspects for PD measurement on stator coils and bars. It's a topic we might not talk a lot, or we may have not been talking a lot, but recently there has been some more and more interest, a growing interest regarding this, so I thought that I could share some practical aspects for this tricky measurement. So for those of you who might be less familiar with stator winding, so here we have a sketch of a hydro generator. This is an horizontal machine. You can see there's a shaft, there's a coupling here for the mechanical device. Then you have the rotor. You have a bunch of poles, and then in yellow you have the stator winding. On the other part of the stator winding, on this picture in the gray part, that's the magnetic core basically. So for a motor, then the stator winding induces a flux in the magnetic core, which is going to create a movement of the rotor, and for a generator is the other way around. When they construct stator winding, they don't come as a complete assembly. They're manufactured coils by coils or bars by bars. I'll share more details a little bit later. But here you have basically a schematic of what we can call a stator coil, right? And those coils are inserted into the magnetic core, and they're connected in series with each other, right? So at the end, you have a complete winding. Machines can have several of these windings in parallel, depending on the size of the machine. Basically here what you have two different types of construction, right? You have, the title of the presentation talks about bars and coils. Today we're kind of going to treat them as the same, but I just want to point some distinctions. So on the left side here, you have what we call a coil, right? So a coil is basically used on smaller and medium-sized machine, and they have several turns within the same component. And you have a picture on the lower left side. While the bars are usually used in bigger machines with higher rating, and a bar is usually referred to as a half turn. And you can see why. It's because once you connect them together, they form a complete turn, basically. For PD on individual component, it's something that might affect the measurement, and we'll talk a little bit about it later. Very quickly, I don't want to spend too much time on that, but I think it's relevant. So how those are insulated is a bit different than a lot of other assets. So yes, it is a tape, an insulating tape, but the main insulation material is basically mica, which is a rock. And being a rock, it is inorganic and highly resistant to electrical degradation. Those different layers of tape basically are wrapped around the conductor, and using different technique, there's VPI, there's enrich, there's global VPI, we're going to fill the gap between the layers of tape with an epoxy resin. That allows as well to increase the thermal conductivity and as well to make that assembly more stable mechanically, basically. The big advantage for using that construction is that if you remember yesterday, I did mention that the time to failure is usually affected by that distance that the electrical tree has to travel or propagate to bridge the gap between the two electrodes. Having those different layers of what I can say PD resistant material increases significantly the path that electrical tree has to travel. And you can see a nice picture here. It's can I have a laser pointer on this?
Yeah.
But that's okay. I'll do without it. So you can see basically on the upper right side that electrical tree growing in the between the layers of tape, and on the lower graph of the upper right side of the screen, it's basically a zoom in, and there's an electrical tree that's initiated in epoxy, and the black line, horizontal line, is a piece of mica, and you can see how that tree just go around it and not through it. And because of that makes PD electrical machine what we call PD resistant. You can in fact have PD in rotating machines for dozens of years, basically, without a failure. Defect on the insulation, when we do PD measurement on individual component, at least for factory testing perspective, it's mainly to get the to detect the voids within the insulation. So basically, if you have wrinkles in your tape and the resin didn't really impregnate it correctly, you're gonna have those voids created and partial discharge activity. And here you have another what we could call delamination here between different layers of tape. So this is really what we're looking for when we do factory testing of those components. To do the measurement itself, it's basically at the surface, it looks very easy. It's nothing more than your typical IC 60 to 70 measurement. That is how it is done the vast majority of the time for individual components. And basically, what you're going to have is that you're going to have your test object connected to your high voltage source, and you're going to have your coupling capacitor and the measuring impedance connected in parallel, basically. In this one, what you can see is that you have the two, what we call the legs of the coil, which are grounded. They're basically how we do that. We use what we call simulated slots, so they can be aluminum plates, steel plate, L angles. There's different methods that are used by different manufacturers and even different utilities. And then the coil leads going to be connected together. This is basically a recommendation. This is not always how it is done. Sometimes only one lead is connected. And I'll talk a little bit more about that in a few slides. Just here's some pictures of how it will look like. So on the left side, it is more on an R&D perspective where you have a stator coil, you have L angles on each leg, you have the high voltage transformer here. We have some sort of corona ring to mitigate partial discharge activity from the lead, and you will have a coupling capacitor connected here that is missing in this picture. On the right side of the screen, this is more in a factory environment, but as you can see, it's very typical, very similar. I mean, you have the simulated slot here by L angle that is supported at different location. Those slots are grounded, and you have the coupling capacitor here and the high voltage transformer. A typical test procedure, this is where things get a little bit more complicated than a typical measurement. Is, as I said, this is something that is growing in popularity, and basically at this time there's no international standard for that provide a test procedure for that basically. So sometimes it is done, it is usually done when it's specified by user, by the customers to the manufacturer. It can be done at the beginning, throughout, and at the end of the two of different aging tests, mainly the thermocycling test and the voltage endurance test. There's other occasion when it is performed on every single component. So that can become very extensive if you have a machine with 400, 500 coils or bars. That can become a big test, basically a big part of the factory acceptance test. So how it is done, the majority of the time, is that we're gonna have two different time of the test or steps. So the first step will be what we call the conditioning. So, and I'll talk more about that later on. So we were gonna raise the voltage to a certain point, either to the maximum test voltage or either above that test voltage for a certain duration of time. Prior, we're gonna start measuring PD. Then we're gonna decrease that voltage, and then we're gonna either redo a similar procedure or we're gonna do step increase and step decrease. You're gonna measure PD at each level, you're gonna measure PD IV and PD EV, so the inception and the extension voltage. I did mention there's no procedure from international or even national standard. If any attendees know any, that would be great. But what we do, we have two main standards for PD, offline PD measurement of rotating machine. There's IEEE 1434 and there's the IEC 634-27-1, which is gonna tell you, provide a lot of information and recommendation as per complete machine. Both guides have and standard have section about individual component, but those are not the focus on those documents. We are coming out with a P2465, which is focused on PD measurement for individual stator coils and bars, and it is there is a recommended procedure in there. So that's going to be, I think it's already available as a trial guide, so you can go get it. Another document that can be useful is the 1799, which deals with what we call external discharges using alternative techniques. So a UV camera, an acoustic camera, things like that, which can be also useful for different types of PD than what we're talking about today. As far as challenges, I mean, I already mentioned that there's no specification from international and national standard, and as you know with PD, there's tons of way that PD can be done on the same equipment for the same reason. So that makes comparison a little bit difficult to do. If, for example, you're a user, you have your own way of doing your PD measurement. Well, if you're buying a winding and you're doing your specification for the coils, if you ask for PD measurement and not go beyond that and not specifying how it's going to be done, there is a lot of chance that it might be done differently by the manufacturer. As I said, insertion of Stator windings are PD resistant, and this is one of many reasons that it is extremely difficult to establish limits. That stands out from other equipment where it is usually PD free or not, right? We talked a lot about cables during this symposium. The maximum charge is 5 picocoulomb, but that doesn't mean that a 3 picocoulomb should pass. This is really a compromise between being able to achieve a sensitivity that allows the 5 picocoulomb. There's been disparities because of that are reported by some users when doing PD tests, right? If you use different PD instrument, if you're using different PD technique, different sensors, even that conditioning period, if one do a PD measurement with and someone else do it without on the same test object, might get different result. And that leads to issue, right? Because if, for example, you're buying if you're buying a machine, you're specifying, let's just say 200 picocoulomb for individual coils, and one equipment gives you 500 and the other one gives you 50, then you have an issue because it becomes an issue because it creates one way to make a test fail or to make it pass, right? Just depending on which equipment you're going to use. So we'll address a few of these points right now. So yeah, let's just start with the disparities between PD instruments. So it all started, I think, a few years ago. We had customers that were using our equipment that were running the specific issue I told you about, having coil that passes with one equipment and rejected with the other equipment. And the thing we need to understand is that, first of all, the whole charge estimation process, right? You need to be compliant with IEC 6270. So first of all, if you have one equipment compliant with that and the other one is not, then there's a big chance that you're going to run into different results. And even if you go into if you have two equipment that are compliant, the old charge estimation relies on the fact that you need to have your FFT content constant for both your calibration poles and your PD poles. And if you have one of these that is not constant in the frequency range that you're measuring, then this is going to lead to inaccuracy in the charge estimation. So let's just run a few scenarios very quickly. If I look at the lower left, if I measure here, right, with the yellow being the frequency spectrum of my calibration pulse and the blue of my PD pulse, then if I measure here in the red, between the red lines, then both frequency content are flat. I will get I'm gonna get an accurate charge estimation. Now let's just say that the frequency spectrum of my PD is not constant within my frequency range that I'm measuring, but the one of my calibration pulse is, I will have an inaccurate estimation. And same thing for the other way around. This is very difficult for large test objects, such as complete windings, cables, transformer, and to that end, the IEEE committees for PD on transformer already took some action regarding that, and they are even more restraining on the frequency range that they allow for their PD test. IEC 6270 goes from 100 kilohertz to 1 megahertz, while for transformer, they're going to recommend between 100 to 200 kilohertz, right? Just because you are more likely to have that flat frequency spectrum in the lowest frequency. So practically, how does it look like when we do measurement on a specific coil, right? So what we did, we had a coil that, and we did simultaneous measurement, and we're lucky we have two different PD instruments in our portfolio, so we compared them at the same time, and we went one step further, we used different sensors with our MPD 800. So what we had one MPD 600 using a 2.2 nanofarad capacitor we had an MPD800 using a 1 nanofarad coupling capacitor, and we have an MPD800 using a 2.2 nanofarad capacitor. And once you do the calibration, you can see that the frequency spectrum is more or less flat in our frequency range that we're measuring, which is the blue here. And once we do our PD measurement, we get PD, and the frequency spectrum is more or less flat. You can see there's a variation, but we're talking in the frequency range 1 or 2 dBs per over the whole frequency range. So it is not that much. And using the simultaneous measurement, we can see that no matter the configuration we have, no matter if we're using an MPD600, no matter if we're using an MPD800, no matter if we're using an MPD800 with a different sensors, we will always get similar results among our 3 equipment. So that was pretty good result, at least for us. It means we can switch PD instrument on those type of assets. The other thing that we did, we wanted a little bit to recreate the situation we ran into, so switching the frequency to something more similar than what the customer was using for comparison. And the issue that we ran into is that basically it's hard for our competitors to give us temporarily one of the instruments. So that's something that we were not able to recreate exactly. But at least what we did, we switched the frequency range a little bit. So for the MPD 800, we increased the frequency ranges up to 700 kilohertz. But for the MPD 600, we switched it a little bit even more, so extending it. So now during the calibration pulse of the MPD 600, we include that big bump here. While for the 800, we're still very constant. The other thing that we did, we can see the same behavior in the measured PD pulse, right? Where we start to be non-linear anymore. We still did the calibration, but because of those non-constant frequency spectrum, this is where we started to get very different results in our measurements. So the 2 MPD 800s, using the same frequency range but different sensors, still measure the same thing. But the MPD 600 now, with a slightly different measured frequency, got almost a 50% error on the measured charge. So we can see it's very easy to get different value just by having slightly different measured frequency. We are looking to expand that to more coil, more bars, more PD instrument, but so far this is what we're able to achieve. So what can be done to improve comparative measurements? Well, try to look for that constant frequency range, and most often they're not. That's going to be altering the settings of the PD instrument you're using, going down in the lower frequency range of what's allowable by the standard or your PD instrument. If it is not possible, and I mean you're going to get an accurate result, and the solution in that case is really to use the same equipment and stick to it with any situation. But that might be complicated when you deal with different suppliers, basically. Applying limits is a little bit, can be difficult for rotating machine, and in general, but also for smaller components like individual coils. For the reason I just stated, that's because you can have different values depending on the instrument or the frequency spectrum that you're measuring, but as well because rotating machines are PD resistant by nature. And we have an experiment that's running right now. We have 3 coils that we're aging at 30 kV, and we had 2 failures. We had a 3rd failure actually this morning, so I haven't had the time to update this presentation. But basically, as you can see in this one, I have 1 coil failing at 823 hours, which with an apparent charge of about 1500 picocoulomb, while my other coil went until 1769 hours with similar PD magnitude, right? And basically failed at 5,000 picocoulomb. So it's difficult at this point, and while the third coil just fell at around the same time than coil number 19. So again, it is very difficult to, just by the value, to say when do you end it, when don't you end it, basically. And the thing is that that might not be too much, but 17 hours and 1,700 hours is a lot at 30 kV when that coil will see 8 kV in operation at max, at the worst case scenario. So you can imagine if you try to correlate that extra 1,000 hour of operating time to the real voltage, that will be a lot of hours that you will be missing out on. Rather than just relying on value, some authors have started to dig into the PRPD diagram. We showed yesterday how it can be useful to mitigate interferences, to find out what type of PD is present, and maybe that's something that can be used as well for Stator coils and bar, in a way that here you have the same aging process that we've seen, that I've showed you before, but with the evolution of the PRPD. And you can see that the main body of partial discharge activity doesn't really change with time starting after 400 hours. However, at the end, we started to see those high magnitude, low repetition rate PD in this case, which could be an indication that you have one of your several PD phenomena in that coil, because coils can have more than one PD active at the same time, but one of them seemed to be getting out of hand at this stage, basically, worsening and worsening. Same thing with the other coil, that basically we can see the main body of PD activity doesn't really increase until right before the end, where you can see those high magnitude PD activity with low repetition rate starting to appear. So analyzing the PRPD might be a better way, or an improved way, of having a pass-fail criteria than just a limit. Conditionings, right? It refers to applying a voltage for a defined period of time, right, before the PD measurement. Basically, I don't know all the details of why the conditioning is needed. Some have speculated that it's because when you have PD activity sustain a small void, the internal pressure will more or less extinguish that PD, right? It's Shanon Lo. It can also be that the surface conductivity going to change as well, bridging that void, right? So those are things that that can affect the PD measurement, but nevertheless, on a practical aspect, we see that pretty often, that if you do not do a conditioning on a Stator coil, you might have something like that, where it is very unstable at each voltage step, and it becomes very difficult to assess using the limit to trend if you're doing a complete machine, or to do a comparison between coils, right? Because at this stage, are you taking the first 5 seconds? Are you taking the middle, the average? Because it's changing by an order of magnitude of almost 2. Doing a conditioning before makes the measurement after that initial decrease in PD magnitude, made that measurement way more stable at each step after the conditioning period. So that is something that more and more people are aware of. However, the conditioning time is not really agreed by everyone. I've heard some utility requiring 10 minutes. I've heard some manufacturer not being too happy about it, because if I take again the example that I introduced at the beginning of a machine with 400 coils, that's a lot of testing time that needs to be added. But if you want to have anything out of it, you should do a conditioning period. Another thing that can be used is to use an average of the QIC value, right? So PD in reading machine, because you have different site, because of the random nature of PD activity, which we introduced a little bit with the availability of the first electron yesterday, is really unstable even when you maintain the voltage, right? You can set the top that PD activity can jump up and down, right, of several hundreds of picocoulomb. If your pass and fail criteria is right on that edge, that can become problematic. Using the average of those values, yes, you will lose some of the sensitivity, however, will make trending and comparative measurement much, much more smoother. I think that I'm getting to the end of the presentation. What to do with those coil leads, right? I mean, the simplest thing to do is really to connect them together. So from my experience, it doesn't really matter on a calibration perspective which end of the coil you're going to connect to. What's going to affect your measurement is really when you do your PD measurement. If you do a PD measurement, you have PD that's closer to one end of the coil than the other. Depending where you install your coupling capacitor, you might have discrepancies, at least for the coils that we tested. And that becomes even more cleaner when you increase the frequency when you measure. Still compliant with IEC 6270, but still on the higher range. It also, when you do comparative measurement, it's also much simpler to have them connected together, so you're making sure that between the coils, if you don't connect them together, one test operator can use one end of the coil, the other one can use the other end of the coil, so it just makes things much simpler. To conclude, those components seem simple, but there's a lot of things that needs to still be resolved. Some of them going to be answered by a new guide, but it is still the first version of this guide, and there are still things that are not addressed, such as limits and different PD instrument, basically. Comparison between test instrument is possible, at least from the same manufacturer, as long as they use the same frequency range. That's, at least from our investigation, that was what stuck out from that. It is recommended to perform a conditioning. I think I've been clear about that. And yeah, if you can, when you do measurement on these components, you should always try to use the lower range of IEC 6270 that allows you to be more stable in the frequency range, basically. And that's it.
Thank you, Mathieu. Very nice presentation for the cases as well. There are actually quite a number of questions here, so let's address that one by one. The first question, I think you sort of addressed that, which is, do you have pass-fail criteria for PD magnitude for hot coil or bars, right? So I think you sort of covered that in the presentation. Yeah. Maybe then the subsequent question is, do you also have limit for a global VPI machine, so VPI installation machine, that vendors must meet for an FAT?
We don't. I know some PD equipment manufacturer are going to have some limits. This is not something that we have been really keen on. I know some manufacturer of Stator coils and bars going to have their own limit as well, and some utilities. The funny thing about that is that everybody seems to have different values for limits, and that basically drives our point a little bit that when you have limit, but they're all different, even sometimes across different manufacturer, at least for us, as right now, it doesn't make sense to have a pure solid limit. Basically.
Yeah. I think that also similarly apply for the 4 kV motor and maybe high voltage 6.6 or 13.8 kV motors. I think there's currently no consensus on having a hard standard on that.
Well, it's even more difficult when we start talking about complete machines. So my presentation was highly focused on individual components that are small. So the effect of attenuation is much more and much less important than a complete machine. A complete machine, you can have, even if you have a 2 nanocoulomb limit, if your PD is occurring at the top of the first coil versus the end of the first coil, you won't measure it with the same magnitude, right? So it becomes very difficult to have limits in this situation.
Okay. Another question, which is more related to standards. Question is, what about EC 634-18-41? So 34 is general rotating machine standards, and 42 for partial discharge in rotating electrical machines.
Yeah, so those standards, I guess that's my mistake. So my presentation is really focused on what we can call high voltage machines. So I would say above 1 kV, above 2 kV. The standards that were mentioned are for what we call PD-free or for smaller machine, basically. So, and I think they govern as well, if I'm not mistaken, PD under impulses, which are, so I think 41 is for PD-free installation system. And the second one is 42 is for PD resistant system, but those are really focused for impulse application.
Yeah, from what I see also on the topic is fed from voltage converters, so the application level will be a little bit different. Another question that is related to also standard. Did you say the PD or is the PD tester that tests Stator coil and winding needs to be IEC 6270 compliant, or both IEC 6270 and IEEE 57.113 compliant?
Yeah, maybe I went a little bit too fast on that. So usually if you're doing a PD measurement, we recommend that you do it according to 6270 for at least for this type of apparatus, so individual component like Stator coils and bars. The IEEE C 57.113 is the PD measurement standard for transformer, which also will follow something similar than IEC 6270, but the frequency range is a little bit more restrained, right? So IEC 6270 goes from 100 kilohertz all the way to 1 megahertz. So that's what's allowable. You can do from 100 to 200 kilohertz, for example, if you want. But you can also do from 100 to 1 megahertz. What C57.113 does is that it recommends to use 100 to 200 kilohertz. So a very narrow band compared to what IEC 6270 does. And at least from our initial experience, that seems to be where you get that constant frequency spectrum on those Stator coils.
Maybe some supplement information. 113 is recommended practice for PD measurement in liquid fuel power transformer and shunt reactors. So the content of it also has, similar, also heavily referring to the IEC 6270 as well. I do think they enlarged the frequency a little bit, but I think in general the principle are very, very similar. Especially they're also heavily referring to the 6270. Anyway, I think there will be a new edition coming up soon because I think the ballot has gone for a few months ago, so there probably will be a new release on that pretty soon. Other question, is the power frequency an issue for PD test consistency? I think that's a great question. For example, factory testing in a country with 50 hertz power frequency, then testing the same product in different destination country with 6 hertz power frequency. Does that give a PD measurement problem? I think that's a great question.
From what I've seen, yes. I've never seen a direct comparison very addressing this specific issue, 50 hertz versus 60 hertz. From what we've seen among, I'll say, larger differences, yeah, there will be, you wouldn't be able to compare. We've seen it as well with using RTS. There's discrepancies, but unfortunately, I haven't seen a direct comparison between 50 and 60 hertz. I will say you're gonna have a difference in PD value, but I'm not 100% sure.
Yeah, but I do understand sometimes this question come up because in some particular country, you know, something like Brazil, 50 and 60 hertz are being used together, right? And then some area is using IEEE standard, but using 50 hertz for some example, right? So then there could be a little bit of a problem to interchange the result. But okay, so I think we have time to maybe address the rest of the question. Two more questions. If you're testing the stator winding of a 4 kV motors, is the testing uniform of all areas of the stator winding system? Is the testing uniform, or test voltage maybe? In other words, are there certain area of a stator winding where PD is more difficult to be detected?
It's so in general, yeah. So if you talk about in general for complete winding, we'll see the further away from the neutral end or the line end. So most PD measurement on rotating machine are done from one end of the machine. So from the what we call the line terminal. So if you have PD, a few coils, and now as you go further away, you lose sensitivity on the PD measurement. So it's gonna get attenuated. However, for 4 kV machines, they're usually much smaller than for example, let's say a hydro generator. And that provides you with, I would say, a better sensitivity. But yeah, the further away, as a general rule of thumb, the further away you go from the line terminal, the more difficult it is to detect the PD. We have done investigation on hydro generator, turbo generator, 13.8 kV machine, and in all those equipment, it was the same result. So I hope I understood the question correctly. But yeah, the further away you go from your measuring point, the harder it becomes.
All right, one last question in the Q&A area. Side question, has there been any discussion between bodies like IEEE or CSA and OMICRON regarding PD testing of transformers under 722 kV class, such as acceptance, partial discharge values, or practical test procedures?
For transformers, I don't think we have ever been involved with CSA. We are involved heavily with IEEE on different working groups, but not with CSA. I do think the new IEEE C5701, I think the general standard for transformer has reviewed their criteria, and I think we're about to have a procedure. We already have a procedure for the transformer you're talking about, so smaller units. So maybe I would say go have a look at that standard, and you should have a procedure there. It's still considered optional, but there's something there,
Yeah. So not that similar, not that I'm aware with CSA. In IEEE, there are discussion with class 1 and class 2 power transformers. So lower than 69 kV, yes, I think there's also already something there with the standard, and they're revising it also. I remember attending one of the meeting also, but between the bodies, I don't think so. I think from IEEE to IEC, there's the TC14 representative, but that's about it.
Yeah, they have liaison committee between IEEE and IHC in different working group, but not CSA. I've never, at least personally, I've never been involved with CSA.
Maybe one last question?
Yeah, sure.
Yeah. So are there non-destructive way to attenuate map a stator winding?
Oh boy, all the times I've done this, I had to drill in the winding at some location. So I don't see, you could always try with an HFCT in the end winding area, injecting a pole, inducing a pulse like that. The only issue is that you will only have you will only have access to the unwinding, and it wouldn't be really representative of, I would say, typical PD activity. That's the only way I can think of right now on the spot.
All right, sounds good. Yeah, just trying to quickly answer the question in the Q&A session, but I think that's about it. We'll come back to everyone on the questions. So I have that marked as well, but we are closing to the end of the session. Thank you very, very much for your active participation. We'll come back to all the questions here. So with that, I think we can close the session. So I'll pass this to Teresa for some closing remarks. But Mathieu and I just wanted to say thank you for all the participants who stay all the way for the symposium today, and then thanks for our speakers to have delivered the excellent presentation as well.
Yeah, thank you everybody.
Yes, awesome, great job. To y'all as well, Mathieu and Mathieu, for supporting and moderating the event and supporting all the Q&A. So I want to thank everyone again, with the speakers, the attendees, and I just want to apologize again with the WebEx glitch. I know that was a little unfortunate, but we did redeem ourselves, and we will be sharing all the presentations from today's session, and we have been recording the session. Right after we're done, we are going to check the recording, make sure it's up to quality, and we would definitely want to provide that for all of y'all. But on the screen is a slide that is similar to the one that I started today in our intro, and it just has some more information of how to stay connected with OMICRON. We want to really thank y'all again for joining us for these 2 days for this PD Symposium. And as I mentioned, once you exit out of here, you will your browser will go to a survey. So please put any of your feedback, good or bad, and any additional information if you would like from OMICRON. But with that, I think we are good to close. We will keep this on the screen a little bit longer, so if you want to go ahead and just take a look at the other ways that you can stay connected with us. But thank you again, and wishing you all a great rest of your week, and we'll see y'all soon. Bye.